The water explodes into motion long before the prey even understands why it is running. There is no warning. There is no subtle shift in the current to telegraph the danger. One moment the ocean is a quiet expanse of suspended blue, and in the next, a school of sardines fractures mid-column. Silver bodies flash in tight, desperate synchronization. Their tiny muscles fire in rapid, frantic oscillation as they surge away from a shadow that simply does not slow down. This is not the sudden, explosive ambush of a reef predator. This is not a hunter that waits in the dark to snap its jaws in a fraction of a second. Behind the fleeing silver mass, a bluefin tuna drives forward with relentless, terrifying propulsion. Its crescent tail slashes through the water in a steady, unbroken rhythm. It is a rhythm engineered over millions of years, not for the sudden spectacle of a short sprint, but for the grueling, inescapable mathematics of endurance. The pursuit has already begun, and it will not end quickly. Tuna are not hunters of surprise. They are hunters of absolute inevitability. To understand the terror they inflict, you have to look at how their bodies are built. They are shaped for sustained speed across vast, unending distances. They possess a fusiform shape, a perfectly streamlined torpedo of muscle and bone that minimizes drag in the densest medium on Earth short of solid rock. Everything about their architecture is designed to slip through the crushing weight of the ocean with zero wasted energy. Their power originates from a massive, heavily muscled caudal peduncle, the thick wrist of the tail, which anchors one of the most efficient and devastating propulsion systems in the entire marine world. While other fish are built to sprint, relying on short, chaotic bursts of speed fueled by anaerobic metabolism, the bluefin tuna operates on a completely different level of existence. They maintain high cruising speeds through a miraculous physiological adaptation known as regional endothermia. Deep inside their bodies, they possess specialized heat exchangers called the rhetia mirabilia. This intricate web of blood vessels acts as an organic furnace, conserving the metabolic heat generated by their dense, dark red muscle tissue. Instead of losing their body heat to the freezing surrounding ocean, the tuna traps it, elevating its internal body temperature far above the water it swims through. This is their ultimate weapon. Warmer muscles contract with terrifying efficiency. It allows the tuna to sustain high-velocity pursuit for hours, long after every other competitor and every single prey item has succumbed to total physical collapse. As the tuna closes a distance, the sardines do exactly what evolution has programmed them to do in the face of annihilation. They cluster. They fold inward upon each other, compressing into a tight, frantic bait ball. It becomes a rotating sphere of thousands of terrified fish, a collective defense mechanism meant to overwhelm the predator's senses. The bait ball presents a solid wall of synchronized, chaotic movement. The sheer density of flashing scales and darting eyes exploits the predator's visual targeting systems, creating a confusion effect. The goal is simple: make it impossible for the hunter to isolate a single individual. It is a brilliant defense against almost anything else in the sea, but it is entirely the wrong defense against the bluefin tuna. The tuna does not care about the confusion of the core. It does not plunge blindly into the center of the mass. Instead, it begins the siege. It slices through periphery, skimming the edges of the bait ball. It forces the school to shift, to compress even tighter, to continuously expend their precious, limited energy. This is a game of attrition. Each evasive maneuver the sardines may cost them. Each sudden burst to avoid the snapping jaws burns through their tiny glycogen reserves. Every frantic acceleration erodes their endurance. The chase is not chaotic. It is a systematic application of strategic pressure over time. Often, the tuna does not hunt alone. They operate cooperatively, a synchronized squadron of endurance hunters. Together, they corral the desperate schools, driving them upward toward the surface or pushing them into confined spaces where their escape vectors narrow and vanish. By alternating sudden bursts of acceleration with smooth, sustained cruising, the tuna maintain terrifying proximity to their prey without ever exhausting themselves. Their cardiovascular system is a marvel of biological engineering. Supported by an abnormally large heart and incredibly dense capillary networks woven through their red muscle, they process and deliver oxygen with unmatched efficiency. They delay fatigue indefinitely. The sardines, lacking these thermal advantages, lacking the massive heart, lacking the heat-trapping veins, begin to break down. The fear in this scenario is profoundly different from a fear of a sudden ambush. It is not the shock of immediate capture. It is a slow, creeping, suffocating realization that distance no longer equals safety. A sardine that manages to slip free of the main cluster, swimming with everything it has into the open blue, will suddenly detect the heavy, rhythmic pressure waves directly behind it once more. The predator has not disengaged. It never disengages. The tuna possesses acutely sharp vision, adapted perfectly for the harsh brightness of the surface and the murky depth below. It tracks individual fish even as the light shifts and fractures. It recalibrates its trajectory with mathematical precision, adjusting its tail beats to maintain the absolute optimal ratio of thrust to drag. The hydrodynamics of this pursuit are a masterclass in physics. As the tuna cuts through the water, it actively reshapes its own body to reduce resistance. It has retractable fins that fold perfectly into specialized grooves along its flanks, creating a smooth, unbroken profile during high-speed chases. Its skin is coated in a slick layer of mucus, further decreasing the friction of the water against its scales. Every anatomical detail transforms sustained pursuit into an energetically perfect strategy. The predator is not gambling its life on a single, explosive lunge. It is investing its biology in duration. As the minutes stretch on, the physiological reality of the sardines reaches a breaking point. Their anaerobic capacity hits its absolute limit. Lactic acid begins to flood their tiny muscle tissues, burning through their fibers and completely impairing their ability to contract. Their swimming becomes sluggish. Their respiratory rates spike violently as they gasp water over their gills, desperately struggling to meet an oxygen demand that cannot be satisfied. The beautiful, fluid cohesion of the bait ball begins to fragment under the crushing weight of metabolic strain. It is no longer a unified organism. It is a scattering of exhausted, dying individuals. The tuna senses this. It can read the subtle changes in the schooling dynamics. It hones in on the specific individuals whose swimming patterns have become erratic, the ones whose bodies are failing them. And then, the tempo of the hunt changes. The tuna accelerates, but it does not accelerate from a resting state. It accelerates from an already sustained, high-speed velocity, pushing its massive body into a terrifying new gear. The prey, completely depleted, suffocating on their own lactic acid, cannot even attempt to match the renewed surge. Capture finally occurs, not because the predator was faster in a single lucky instant, but because the predator simply outlasted its target. The final bite is swift, violent, and absolute, but it is merely the culmination of a long, drawn-out process of sustained attrition. The ecological ripples of this hunting style are immense. This relentless method of predation exerts so much pressure on prey populations that it fundamentally shapes how they school, how they behave, and how they migrate across the oceans. Sardines and other small pelagic fish are forced to constantly balance their desperate need to feed with the overwhelming need to avoid being run down. They are forced to travel in these massive, dense aggregations, sacrificing their individual anonymity to reduce their personal risk, even though it increases their collective visibility. And the bluefin tuna tracks these massive aggregations across the vast expanses of the open ocean. They migrate seasonally, following the shifting distributions of their prey. Their legendary endurance allows them to traverse entire oceanic basins, linking distant ecosystems separated by thousands of miles of empty water. They are the circulatory system of the ocean's food web. But even a creature this magnitude, a predator so perfectly designed that it seems invincible, is bound by constraints. The narrative takes a dark, inevitable reversal when you consider that this relentless hunter is tethered to the physical limits of the planet. To fuel their massive hearts, their heated muscles, and their unyielding speed, tuna require incredibly high concentrations of oxygen. They are addicted to it, and as the global oceans warm, the dissolved oxygen levels in the water begin to plummet. The suitable habitat for these kings of endurance is compressing, shrinking vertically and geographically. The very physiological marvel that grants the tuna its absolute dominance also ties it to incredibly narrow, fragile environmental parameters. In waters depleted of oxygen, their legendary endurance begins to evaporate. Their advantage diminishes. The furnace cools. Furthermore, the open ocean holds a predator that the tuna cannot outswim. They are among the most heavily targeted fish by human industrial fisheries. Miles of long lines and massive purse seine nets are dropped directly across their ancient migratory routes. This applies a completely different kind of sustained pressure. The ultimate hunter of the open blue suddenly becomes a hunted, pursued across the oceans by massive vessels equipped with high-tech sonar and satellite tracking systems. The tuna's blinding speed, its endurance, its heat-exchanging blood, the ultimate shield against natural predators, offers absolutely no defense against the cold calculus of technological pursuit. Yet, when you look away from the nets and look back down into the untouched blue, the sheer perfection of the tuna's design remains staggering. Their red muscle fibers, so incredibly rich in myoglobin, store oxygen with ruthless efficiency, supporting prolonged aerobic activity that defies belief. Their massive gill surface area facilitates rapid gas exchange, filtering the ocean for every available molecule of air. Their streamlined morphology ensures that every single unit of energy spent translates directly into forward distance. Every single anatomical detail converges toward one singular, terrifying strategy: never stop. For the sardine caught in their path, the terror is cumulative. It builds with every passing second. It is not a fleeting shadow that vanishes after a single misstrike. It is a looming, physical presence that persists, a presence that seamlessly adjusts its pace, that mathematically recalibrates its distance, that patiently waits for the prey's biology to inevitably fail. In the face of a bluefin tuna, escape is never a solution. It is only ever a temporary reprieve. The predator's immense patience transforms time itself into a weapon. Even out in the vast, seemingly limitless openness of the pelagic zone, where there are no coral walls, no rocky overhangs, and no mangrove roots to trap a fleeing fish, confinement still emerges. It emerges through total exhaustion. The ocean offers infinite space, but that space does not equal a sanctuary when your pursuer effortlessly matches your every single turn. The tuna's massive body, shimmering in a brilliant flash of metallic blue and silver, cuts through the water with a cold, unstoppable consistency of machine. Its muscles are warm, primed, and flooded with oxygen. As the sardine's energy reserves finally, totally collapse, its swimming pattern inevitably stutters. The great silver school no longer moves as a single, defensive organism, but scatters into broken fragments. The tuna senses a final vulnerability and commits to the ultimate acceleration. Its jaws open, engulfing the broken prey in a single, decisive snap. It is a sudden end to a pursuit measured not in seconds, but in the slow, agonizing application of sustained pressure. And then the sea calms. The water stills. The predator resumes its steady, unbroken cruise, its giant eyes scanning the blue for the next aggregation. There is no frantic feeding frenzy. There is no chaotic display of dominance. There is only the quiet, terrifying confidence of a creature built to endure forever. In this open realm, fear is not the instant of impact. Fear is the suffocating knowledge that the chase will never, ever cease. The predator will not tire first. The ocean is vast, but stamina reshapes its very boundaries. And somewhere just ahead, miles away in the blue, another school of silver senses a faint disturbance in the water, completely unaware that distance alone will never be enough to save them. The first penguin stands at the very edge of the world. Katabatic winds, born in the high, frozen interior of the continent, poured down the ancient glaciers, pressing it stiff, overlapping feathers utterly flat against a body that was engineered entirely for water, yet currently finds itself stranded on unyielding stone and ice. Beneath the sheer, jagged drop of the ice shelf, the sea looks deceptively calm. It is a vast, heavy sheet of fractured light, trembling slightly against the curved horizon of the ocean. But the hesitation at the precipice is never theatrical. It is not cowardice. It is profoundly, fundamentally neurological. In that agonizingly narrow pause before the leap, an entire, complex evolutionary calculation is unfolding inside a skull no larger than a clenched fist. The bird cannot see what waits below. It is standing on a threshold between two completely incompatible dimensions. From above, the water is a mirror, reflecting the harsh glare of the sky and the towering white of the icebergs. From within, it is an infinite void. The penguin knows, with the absolute certainty of inherited instinct, that once it pushes off the ice, there is no turning back. Gravity will immediately surrender its authority to the ruthless laws of fluid mechanics. Buoyancy will seize total control. Drag will dictate every single trajectory. There will be no mid-air reconsideration. The leap is a total, irreversible commitment. And commitment in this specific, brutal ecosystem is the absolute difference between feeding your young and becoming food yourself. Penguins are the ultimate masters of a paradoxical existence, forced to navigate two entirely incompatible worlds. On land, they are awkward, upright, slow, and completely exposed to the elements. They expend massive amounts of energy just maintaining their core body temperature against winds that scour the Antarctic coastline, burning through their precious caloric reserves while shuffling across the ice. But in the water, that awkwardness vanishes instantly. They transform into living torpedoes. Their wings, useless for aerial flight, have been radically reshaped by millions of years of selective pressure into rigid, highly efficient hydrofoils. These flippers are capable of generating massive lift and forward thrust simultaneously, slicing through the water with the precision of a scalpel. Their internal architecture is a masterclass in aquatic adaptation. Unlike the hollow, lightweight skeletons of flying birds, penguin bones are incredibly dense and heavy. This is not a flaw. It is a vital necessity. It reduces their natural buoyancy so that their deep dives are not wasted in exhausting, continuous battles against flotation. They do not fight the water to stay down. They sink into it with purpose. Their massive pectoral muscles, anchored firmly along a heavily reinforced sternum, drive stroke after stroke, converting metabolic fuel into explosive forward momentum with startling, ruthless efficiency. But all of this biological mastery is useless until they cross the threshold. The transition point, the exact instant of entry, is a terrifying, blind barrier. Light behaves treacherously at the surface of the sea. As sunlight strikes the ocean, it refracts unpredictably, bending and scattering into chaotic angles that completely distort depth perception. From the penguin's vantage point on the high ice, the water actively conceals its interior, but from below, the optical physics flip into a deadly asymmetry. Anything, absolutely anything, that crosses that luminous membrane from the air into the water is instantly outlined in stark, undeniable silhouette. This terrifying imbalance of light shapes the behavior of every single creature on the ice with ruthless precision. Penguins do not simply amble to the edge and tumble casually into the sea. They gather, they shuffle, they wait in agonizing, built-up tension. Hundreds, sometimes thousands of individuals cluster tightly at the very brink of precipice. Their dark backs absorb the faint, desperate solar radiation, while their pristine white bellies flash brightly against the snow. This distinct coloration, known as countershading, is not an aesthetic accident. It is highly advanced optical camouflage. If you look at a penguin from below, its white belly blends perfectly with the bright, sunlit ceiling of the surface. If you look at it from above, its dark dorsal side dissolves seamlessly into black, inky depths of the deep ocean. But this brilliant camouflage is utterly useless while they are standing on the ice. It only activates upon immersion. Before that happens, the penguin must make the agonizing decision to jump. The prolonged hesitation at the edge is almost always misinterpreted by human observers as timidity or fear. In biological truth, it is the highest form of risk distribution. By crowding together at the edge in a dense, shifting mass, the penguins are actively reducing their individual probability of being eaten through a mathematical concept known as the dilution effect. If a massive leopard seal is silently patrolling the dark waters directly beneath the ice shelf, it is lethal, but it is singular. It cannot strike them all at once. Yet, the brutal reality remains. Someone must jump first. The initial diver carries the heaviest burden of the colony. That first bird breaks the informational barrier. Its plunge into the unknown triggers an instantaneous, massive cascade of movement. The subsequent eruption of bodies is not blind panic. It is social facilitation, a deeply wired neurological response where one individual's bold action instantly reduces the perceived cost of risk for everyone else around them. The group transforms from a collection of hesitant individuals into a massive, probabilistic shield. The first bird dives, and the sky rains penguins. The moment they hit the water, the physics of their existence shifts abruptly and violently. the air that was carefully trapped deep within their dents. Overlapping feathers instantly compresses under the crushing weight of the sudden water pressure. This rapid compression reduces their thermal insulation, exposing them to the biting cold, but also crucially minimizes their buoyant drag. Penguins manage this precarious balance with remarkable subconscious control, preening their feathers on land to trap precisely enough air for a thermal buffer, while desperately avoiding any excess flotation that would waste their energy during the rapid descent. Inside their bodies, an equally dramatic transformation occurs. Their blood chemistry fundamentally alters to support the dive. Their heart rate drops precipitously in a state of controlled bradycardia, shunting oxygen-rich blood away from their extremities and directing it exclusively to their most vital organs. Their muscle tissues are flooded with abnormally high concentrations of myoglobin, a specialized protein that stores massive amount of oxygen directly within the muscle fibers, effectively turning their bodies into self-contained biological batteries for underwater propulsion. Yet, all of these internal adaptations cannot erase the sheer, terrifying uncertainty of the ocean. The water column is not an empty swimming pool. It is a complex, three-dimensional labyrinth, endlessly layered with invisible gradients of temperature and salinity. These layers act like fluid lenses, bending the transmission of both sound and light, creating zones of perfect clarity that suddenly give way to blinding distortion. Visibility can collapse from 50 meters to zero within the span of a single heartbeat, and the predator waiting in that water does not actually need to be visible. It merely needs to be present. Leopard seals and transient orcas exploit this threshold with calculating, terrifying ruthlessness. They do not hunt in the open blue. They patrol specifically beneath the jagged edges of the ice shelves. They cruise in the dimness, their massive, dark forms perfectly camouflaged against the depths, scanning the bright, luminous ceiling above them. They are waiting for the unmistakable, high-contrast silhouette of a descending penguin. To the predator's retina, perfectly tuned by evolution for contrast detection rather than fine detail, any sudden downward motion is immediately interpreted as an absolute opportunity. When the predator initiates its attack, the acceleration is entirely vertical, driven by the explosive power of massive axial musculature. The strike is not chaotic. It is not a frantic thrashing in the dark. It is cold, hard geometry solved in fluid motion. A leopard seal can accelerate from a dead drift to lethal velocity in the space of a few feet, its massive jaws opening to reveal teeth designed specifically to grip and shred struggling prey. But here is where the narrative sharply reverses. The penguin's leap into the abyss is never a blind surrender to fate. It is a highly calculated maneuver, fundamentally shaped by the same hydrodynamics that the predator must respect. Penguins do not enter the water straight down. They enter precise, optimized angles calculated to maximize their initial forward velocity, while utterly minimizing their splash signature at the surface. The less disturbance they create, the less tracking data they provide to the hunters below. Some species take this evasion even further, launching themselves out of the water in spectacular, soaring arcs known as porpoising. They break the surface repeatedly, flying through the air for brief seconds to take rapid, gasping breaths, before plunging back beneath the waves without ever losing a fraction of their forward speed. This remarkable behavior drastically reduces the total time they spend lingering in the highly vulnerable boundary layer near the surface, where predators are most likely to strike from below. What looks to the untrained eye like a frantic, playful skipping across the waves is actually ruthless energy optimization. It is a physics of survival, reducing drag by alternating rapidly between the heavy fluid of the sea and the frictionless void of the air. The true fear in this environment is not the attack itself. By the time the attack registers, it is usually too late for fear. The true terror is the invisibility. In the polar regions, the water is incredibly rich with life. Plankton blooms and suspended particulate matter scatter the incoming sunlight, creating a dense, visual fog that obscures everything beyond a few meters. Sound, however, travels 4 times faster in water than it does in the air, but also refracts across the thermal layers, bending away from predictable, linear paths. A penguin diving into this soup cannot rely solely on its sight. It must feel the ocean along its body. The penguin possesses sensitive feather follicles and mechanoreceptors that function much like the lateral line system of a fish. They can physically detect the microscopic, subtle vibrations of a massive body displacing water somewhere in the gloom. The penguin's brain instantly integrates these faint tactile signals, processing the invisible pressure waves into split-second directional adjustments. The neural pathways connecting their visual cortex directly to their motor output are aggressively streamlined for maximum speed. In this icy darkness, reaction time is not just an advantage. It is the absolute definition of survival. Yet, the predators waiting in the deep face severe constraints of their own. Rapid, vertical acceleration demands an immense, punishing expenditure of metabolic energy. A leopard seal is massive, and pushing that bulk upward at high velocity burns through calories at an alarming rate. A missed strike is not just a disappointment. It is a significant energetic cost in a harsh environment where prey availability fluctuates wildly with the seasons. The predators cannot afford to miss repeatedly. Because of this, the penguins time their entry into the water strategically. They often wait for specific periods when the predator density is historically lower, or they delay until their group size swells to numbers so massive that the dilution advantage becomes mathematically overwhelming. During the peak breeding seasons, the synchronized departures from massive colonies effectively short-circuit the predators. A leopard seal looking up at a ceiling raining with 10,000 identical, fast-moving silhouettes is overwhelmed by target saturation. There are simply too many targets at once to lock onto a single trajectory. This is not chaos. It is highly complex, emergent coordination driven entirely by evolutionary selective pressure. The leap also represents a massive metabolic gamble. On land, the penguins are constantly burning their internal energy just to maintain their body temperature against the howling katabatic winds that scour the ice. But in the water, despite the freezing temperatures, their heat loss can actually be slower due to their incredible waterproof insulation and the sheer hydrodynamic efficiency of their movement. However, to feed themselves and to return with regurgitated sustenance for their waiting chicks, they must fully immerse themselves in the danger zone. The fish and the krill they depend on form incredibly dense shoals far beneath the ice, their distribution dictated by deep nutrient upwelling and seasonal phytoplankton blooms. Avoiding the water entirely is not an option. Starvation is a certainty on the ice. Survival is a possibility in the water. Therefore, the hesitation at the edge is never about avoidance. It is about calculation. Consider the profound sensory paradox at play in this daily ritual. From the penguin's high vantage point, the surface of the ocean is utterly opaque. From the predator's vantage beneath the waves, the surface is brightly translucent. This massive inversion of perspective entirely defines the predator-prey dynamics in marine ecosystems across the globe. The brilliant counter-shading of the penguin evolved precisely because of this specific optical structure. The leap off the ice becomes a daily, high-stakes ritual acknowledging the unforgiving physics of the sea. And then, once submerged, if they survive the initial gauntlet, the penguin truly transforms. The stubby wings that once propelled their ancient ancestors through the sky now slice through the dense water with terrifying precision. Their stroke cycles generate powerful lift on both the downstroke and the upstroke, effectively allowing them to fly underwater. Unlike the flexible wings of flying birds, the skeletal architecture of the penguin's flipper completely resists bending under the immense water pressure. It maintains its perfect hydrofoil shape even at crushing depths. Penguins can reach staggering underwater velocities, easily outpacing many of the fish they hunt, and frequently evading apex predators through sheer, unmatched agility. The extreme vulnerability of the jump is directly counterbalanced by their total dominance in motion. There are countless moments when the predators simply miscalculate. A leopard seal lunges from the depths with terrifying speed, its jaws snapping shut, only to grasp a swirling cloud of empty bubbles as the penguin veers laterally with explosive, physics-defying force. Even when highly intelligent orcas attempt to herd penguins against the flat walls of the icebergs, individual birds frequently slip through the chaotic turbulence, carving unpredictable, razor-sharp trajectories that the massive whales simply cannot follow. The very same water that hides the predators also actively disrupts their precision. Deep currents constantly swirl around the submerged bases of the icebergs, creating powerful, invisible eddies that bend and distort pursuit paths. The ocean is never a stable, predictable battlefield. It is a dynamic, violently fluid medium. Still, despite their agility, despite the counter-shading, despite the target saturation, uncertainty remains a defining, inescapable emotion of the ice edge. Evolution cannot entirely eliminate risk. It can only provide the tools to manage it. The penguins standing tightly packed on the ice are acutely aware, through deep instinct and inherited neural circuitry, that the water before them is both their larder and their abyss. Their long, agonizing pause is a silent, internal negotiation with the absolute unknown. When the first bird finally leans forward past the point of balance, gravity instantly takes command. The streamlined body arcs downward, stiff feathers slicing silently through the freezing wind, and then the dark surface breaks with sharp, muted crack as the heavy fluid of the sea suddenly replaces the air. From that exact millisecond, retreat is physically impossible. The buoyancy patterns shift instantly. The bird must fully commit to depth or to speed. There is no hovering between the states of air and water. The ultimate threshold has been crossed. This is the pure essence of the leap. A total, irreversible transition between two worlds governed by entirely different physical laws. The air allows for hesitation, for pausing, for breathing. The water demands forward momentum, or it demands death. Hours later, as the colony returns from their deep feeding trips, their bellies heavy and distended with fish, the entire deadly cycle repeats itself in reverse. Now, the penguins must erupt from the sea back onto the safety of the ice. They evade the patrolling predators in the final, terrifying meter water through massive, ballistic launches. They beat their wings with anaerobic fury, converting their extreme underwater velocity into explosive, airborne momentum, rocketing out of surf and crashing down onto the solid ice. The exact same physics that endanger them on the way down becomes their ultimate shield on the way up. Speed becomes their armor. The ecological implications of this daily cycle ripple outward, altering the very chemistry of the ocean. Penguins actively regulate the massive krill populations, indirectly influencing the entire phytoplankton dynamics through deep trophic cascades. Their thousands of dives redistribute vital nutrients vertically through the water column, as they excrete waste that effectively fertilizes the coastal ecosystems. In turn, the predators that target the penguins shape the distribution of the colonies, fundamentally altering where grazing pressure falls across the entire marine food web. The solitary leap into uncertainty is never just an isolated moment of drama. It is a critical, structural component holding together the entire polar ecology. And so, the scene inevitably returns to the edge. A long, dark line of penguins gathers against the blinding white of the ice, staring down at the abyss beneath them. The sea remains perfectly, terrifyingly inscrutable, simultaneously concealing freezing currents, lurking predators, and the absolute necessity of food. The hesitation stretches out, not as a display of weakness, but as undeniable evidence of mind exquisitely attuned to the exact calculations of risk. When one bird finally tips forward, falling into the void, the rest of the colony follows in a massive, roaring cascade of black and white arcs. They surrender themselves entirely to a fluid medium that may conceal their sudden death, yet guarantees their only chance at survival. The ocean never, ever reveals what waits below. That cold opacity is the only constant. But the leap, repeated generation after generation against all odds, embodies a profound, undeniable biological truth. Life in this extreme world persists not by safely eliminating uncertainty, but by leaping directly into it and mastering the fall. The grip lands before the prey even understands it has been touched. One instant, a crab is cautiously picking his way across the rippled sand, its antennae sweeping the current, tasting the water for the faint chemical traces of food. The ocean around it seems perfectly normal, bound by the familiar, predictable rules of gravity and distance. And in the very next fraction of a second, the water itself seems to seize it. Arms erupt from a seemingly empty crevice with silent, terrifying precision. This is not the explosive, kinetic strike of a barracuda. It is not a predator in open pursuit, launching its body mass through the water. It is an unfolding. The octopus emerges like a complex, biological trap that has already calculated the geometry of the encounter and decided the inescapable outcome. The hunter does not lunge blindly to inflict a fatal wound. It envelopes, Within the span of a single heartbeat, 8 muscular limbs flow over crab's armored shell and defensive claws, sliding effortlessly into every available crevice, anchoring along the rigid joints, and meticulously mapping every single contour of the prey's resistance. The true, paralyzing fear of this encounter is not the anticipation of a bite. It is the immediate, total, and absolute loss of bodily autonomy. Movement instantly ceases to belong to the prey. An octopus arm is not merely a limb. It is a marvel of distributed, alien intelligence. 2/3 of the animal's neurons are not located in its central brain, but spread throughout its arms. Each tentacle contains a dense, highly sophisticated network of nerve tissue capable of independent processing. This allows the limb to probe, to taste, to feel, and to react to stimuli without ever waiting for a centralized command from the head. The arms are thinking for themselves. The underside of these arms is lined with hundreds of suction cups, but to call them simple cups is a massive biological understatement. Each individual sucker is a complex muscular hydrostat, functioning much like a human tongue, but equipped with highly sensitive chemical and tactile receptors. They do not just feel the crab's shell, they actively taste it. When a cup presses against a surface, specialized circular muscles contract violently, physically expelling the water from the cavity and creating an intense, localized negative pressure. The seal is instantaneous. Once engaged, the suction cup does not simply cling to the prey. It locks. Breaking that vacuum requires a sheer physical force that most prey animals simply cannot generate, especially without the necessary leverage. And control escalates exponentially because the octopus never relies on a single anchor point. Hundreds of these sentient, tasting cups coordinate in overlapping, shifting patterns, distributing an unbearable pulling force across the entirety of the prey's body. If the crab snaps its claw defensively, that singular snap is immediately met with dozens of new points of contact that dynamically shift, absorb the kinetic energy, and instantly reattach. The crab's rigid shell, heavily calcified and perfectly designed by millions of years of evolution to deflect the piercing bites of fish or the crushing blows of shorebirds, offers absolutely zero defense against this omnidirectional compression. The armor becomes a trap. The octopus manipulates its limbs into incredibly complex, fluid positions that systematically reduce the crab's torque potential, completely neutralizing any leverage long before the prey can even attempt to apply it. This terrifying advantage is born from the octopus's lack of a skeleton. Its musculature is composed almost entirely of soft tissue, meticulously arranged in longitudinal, transverse, and oblique fibers. This unique, three-dimensional architecture permits a level of extraordinary flexibility found nowhere else in nature. The arms can bend, twist, and elongate at any exact point along their length, completely free from the rigid constraints of bone and joint. It allows force to be applied in bizarre, constantly shifting vectors. When a terrified prey violently attempts to pull away, the octopus does not engage in a rigid tug-of-war. Instead, it tightens selectively. It increases the crushing pressure on specific, vulnerable joints while simultaneously maintaining a yielding, elastic grip everywhere else. Control becomes a fluid, dynamic negotiation rather than a static wrestling match. The neurological dimension of this fatal embrace is equally decisive. The central brain of the octopus integrates the massive influx of tactile and chemical information from its 8 arms in real time, instantly identifying the structural weak points in the prey's anatomy. In crustaceans, this almost always means targeting the delicate articulation between the rigid carapace segments or the softer, vulnerable membrane located near the mouth parts. Concealed at the very center of this writhing cluster of arms is a razor-sharp, parrot-like beak. It remains perfectly poised, but the octopus is a creature of meticulous process. Total immobilization must precede penetration. The predator prioritizes absolute restraint before delivering the final, chemical blow. When the beak finally pierces the soft membrane, it delivers a venomous saliva laced with powerful neurotoxins. These complex proteins are designed to aggressively disrupt neurotransmission in the prey. They flood the nervous system, binding rapidly to receptors at the synapses and preventing the electrical signals required for muscle contraction. The resulting loss of control is not a gradual weakening. It is immediate and catastrophic. The prey's motor patterns evolved over millennia to respond to directional threats, to run away from shadow, to turn and face an attacker, fail completely under this omnidirectional constraint. There is no singular, defined attacker to face. There is no predictable, linear trajectory to evade. Every single movement, every desperate twitch meets absolute, intelligent resistance. The octopus anticipates the recoil of the crab, absorbing the frantic energy through its flexible arms, yielding just enough to prevent injury, and then immediately reasserting crushing pressure. The prey's nervous system enters a state of total overload. Frantic survival signals fire in rapid, chaotic succession as the muscles strain helplessly against the unyielding suction. But as the venom takes hold, the physical restraint gives way to biochemical domination. The neurotoxins interfere with the sodium channels in the nerve membranes, physically blocking the electrochemical language that tells the muscles to move. Paralysis follows. It is not a brutal, physical shutdown of the organs. It is a highly targeted interference with the very circuitry of life. The prey's movements weaken, stutter, and then permanently cease. This terrifyingly efficient strategy reflects a fundamental ecological truth about the octopus. It hunts this way because it has to. In the highly complex substrates of coral reefs or rocky, debris-strewn seafloors, raw speed is frequently far less valuable than absolute grip. Octopuses are the ultimate ambush predators, rely entirely on perfect camouflage and extreme proximity rather than high-speed pursuit. Their skin is an engineering marvel, packed with specialized cells, chromatophores, iridophores, and leucophores, that allow for instantaneous, localized changes in color, pattern, and physical texture. They can mimic the appearance of algae, sand, or jagged coral so seamlessly that they effectively cease to exist as a separate entity. They become the reef. Prey constantly wander within mere inches of their doom, completely unaware that the algae-covered rock they are grazing on is actually a living, breathing, hyper-intelligent predator. The attack ultimately unfolds within a spatial scale measured in millimeters rather than meters. Yet, the apparent helplessness of the crab in this scenario conceals a fascinating, ongoing evolutionary arms race. Crabs and fish are not simply passive, waiting victims in the timeline of history. Many species have developed highly specific reflexes triggered solely by tactile stimuli, designed entirely to disrupt the octopus's inescapable hold. Some crabs will violently autotomize their own limbs, instantly amputating a trap claw to escape the embrace, exploiting the octopus's distributed grip by leaving and holding a severed, twitching appendage while the main body drops away into the current. Certain species of reef fish secrete a thick, highly viscous mucus that drastically reduces friction, making it incredibly difficult for the octopus's suction cups to maintain their negative pressure seal. Even the venom is not a universal guarantee. Prey species continuously exposed to the specific predation pressure slowly evolve partial biochemical resistance, prolonging their survival time and turning the ambush into a dangerous, protracted struggle. And this highlights the great reversal of the octopus's existence. The hunter itself operates under severe, life-threatening constraints. Its incredibly soft body, while granting it unmatched flexibility and the ability to squeeze through impossibly small crevices, offers absolutely zero physical protection against a counterattack. A crab's remaining claw, if not isolated and immobilized immediately, can easily sever a delicate tentacle or gouge an eye. While the octopus possesses a miraculous ability to regenerate lost limbs, that process demands a massive, costly investment of metabolic energy. Therefore, every single predation event carries a significant, calculated risk. The octopus must calibrate its force with absolute precision, avoiding self-injury, while securing the prey as swiftly as physically possible. Furthermore, the mechanical perfection of the suction cups is highly sensitive to the environment. They require relatively smooth or at least stable surfaces to generate their vacuum in highly turbulent conditions, or if the prey manages to thrash violently in a strong cross-current, maintaining the hundreds-point seal becomes physically exhausting. If a few cups detach, the prey might gain the leverage needed to break free. The octopus must constantly compensate, dynamically redistributing its grip across a struggling body, a task that requires immense neural coordination and rapid muscular endurance. Immobilization is never just a singular finished act. It is an ongoing, highly active physical negotiation of force. But the greatest vulnerability of the octopus is exposure. The act of wrapping itself entirely around its prey fundamentally compromises its greatest defense, It's camouflage. The moment it flares out its arms to engulf a crab, it breaks its disguise. It transforms from an invisible piece of the reef into a large, conspicuous, writhing mass of exposed protein. During active feeding, the octopus is highly distracted, its visual and tactile focus entirely directed inward toward the struggling prey. In this specific moment, the hunter risks becoming the hunted. The reef is patrolled by massive, heavy-jawed predators. Moray eels, large groupers, and reef sharks constantly scan the coral for exactly this kind of vulnerability. A distracted octopus, lacking a shell, lacking venomous spines, and lacking the ability to flee while grappling, is a highly prized meal. Even the octopus's famous defense mechanism, the deployment of a blinding ink cloud, is far less effective when its arms are completely tangled with a heavy, struggling crab. This ever-present tension heavily dictates their behavior. Octopuses rarely consume their prey out in the open. Instead, the moment the crab is paralyzed, the octopus will drag the immobilized body backward, retreating deep into a pre-selected, highly defensible den carved into the limestone or tucked beneath a massive boulder. Only within the dark, tight confines of the secure space will the octopus slowly, methodically begin to dismantle the crab, minimizing its own exposure to the wider, hostile ocean. These dens, over time, become littered with the discarded, empty carapaces of thousands of crabs, creating visible graveyards that reveal the sheer scale of the octopus's predation patterns. By aggressively targeting specific populations of crustaceans and mollusks, octopuses act as vital regulators of the benthic community structure. They single-handedly control the densities of crabs that would otherwise overgraze the delicate algae, fundamentally altering the grazing pressure and shaping the overall health and dynamic balance of the entire reef system. The silent, violent immobilization of one single crab echoes outward, maintaining the equilibrium of the entire underwater ecosystem. The terrifying essence of the octopus's grip stems purely from its sheer comprehensiveness. The prey is not merely struck or bitten or chased. It is completely enveloped in a living, multi-sensory net that intuitively anticipates and counters every single point of resistance. The highly distributed intelligence of the arms allows the predator to solve complex, mechanical puzzles in real time. If a crab lifts its heavy claw in a final, defensive posture, the octopus does not fight the stranded claw. It gently, relentlessly rotates the joint backward until the muscles can no longer physically exert force. If a fish flares its gills to breathe, an arm smoothly presses the gill cover closed, silently reducing the oxygen intake and accelerating the exhaustion. Every single defensive movement is mapped, understood, and perfectly countered before it can even become effective. In this realm, softness, which is universally perceived as a fatal vulnerability in a world of teeth and armor, reveals itself to be the ultimate strategic superiority. Without rigid bones to limit its form, the octopus effortlessly molds itself to the exact shape of the prey, eliminating any microscopic gaps that could potentially serve as escape routes. The absence of a skeleton allows the predator to infiltrate the narrowest crevices, extending its total control far beyond the visible, physical boundaries of the encounter. What appears to be incredibly fragile flesh is, in actual, lethal fact, highly adaptive, inescapable fluidity. In the quiet, undisturbed aftermath of the feed, the octopus resumes its legendary stillness. The soft, flexible arms slowly retract, folding back into themselves. The complex array of chromatophores fires, instantly matching the color and texture of surrounding stone, and the predator completely dissolved back into the rock, vanishing from reality. The violent, desperate seizure leaves absolutely no trace behind, except for a hollowed-out, fragmented shell slowly drifting to the sandy floor outside the den. The ecosystem seamlessly resets. The current washes the scent away, and the invisible hunter waits for the next unsuspecting wanderer. Control in the ocean does not always belong to the creature that dominates the open distance with blinding speed. It belongs to the creature that dominates the immediate, intimate space. The octopus does not chase relentlessly. It waits with the patience of stone, and then it collapses every single possibility of freedom into absolute biochemical inevitability. When its soft arms finally close around you, the escape routes vanish, not because they're physically blocked by a wall, but because they've been entirely absorbed into a living, thinking net of muscle and nerve. The prey's final fear is a sudden, dark realization that movement itself no longer answers to its own commands. In that exact instant, the ocean's fluid, boundless openness irreversibly transforms into the tightest, most inescapable confinement on Earth. And within that dark confinement, the octopus reigns supreme, conquering not through brute strength or sudden speed, but through profound, terrifying mastery of intimate touch and total, yielding pressure. The water is perfectly, hypnotically still when it happens. A massive shoal of sardines drifts through pelagic blue, moving in a tight, fluid formation. Thousands of silver bodies are perfectly aligned in a subtle, beautiful synchrony. Every single fish is adjusting its position by microscopic fractions of fin stroke, reading the minute pressure changes of the water to maintain perfect spacing with its neighbors. The sunlight filters down to the surface in shifting, ethereal columns, illuminating the suspended plankton so that it flickers like dust motes floating in a vast, silent cathedral of blue. There is no tremor in the water. There is no sudden shadow to darken the light. There is absolutely no ripple of warning. And then the stillness violently ruptures. A silver lance tears through the center of the shoal with such overwhelming speed that the motion barely registers on the optic nerve. It is less a physical movement and more a sudden, terrifying absence. One sardine is simply gone, erased from the water column before the rest of the school can even begin to contract. The barracuda has already passed through. Barracudas do not advertise their intent. They do not circle ominously, and they do not engage in the grueling, prolonged marathon chases of the bluefin tuna. Their bodies are built like living projectiles. They are elongated, intensely rigid, and hyper-streamlined to reduce hydrodynamic drag in a medium that is hundreds of times denser than air. Their large, terrifying jaws extend far forward, armed with rows of interlocking, dagger-like teeth. These teeth are not designed for grinding, and they are not designed for simply gripping struggling prey. They are designed exclusively for slicing. They are biological scalpels meant to cleanly sever flesh and bone in a fraction of a second. The musculature running along the flanks of the barracuda is completely different from the dark, oxygen-rich red muscle of the endurance hunters. A barracuda is packed almost entirely with pale, fast-twitch muscle fibers. These tissues are capable of utterly explosive, instantaneous contraction. They can generate a terrifying amount of thrust in a single heartbeat, but they are completely unsustainable for prolonged effort. Barracudas are the ultimate sprinters of the pelagic corridor. They are organisms optimized entirely for that one singular fraction of a second when sheer acceleration completely eclipses perception. The mechanics of this strike begin long before it is ever visible. Barracudas are masters of hovering. They hang in the water column in a state of apparent inertia, maintaining their exact depth and position with the absolute minimum of fin movement, drastically reducing their hydrodynamic noise. They become silent, invisible, unexploded ordnance. Their eyes are disproportionately large relative to their sleek body size, and crucially, they are forward-facing. This grants them incredible binocular overlap and pinpoint depth perception. In the crystal-clear tropical and subtropical waters where they usually patrol, visibility can easily extend for dozens of meters. In this bright, open arena, contrast becomes a primary trigger. The barracuda waits for a flaw in the matrix. A single flicker within the massive shoal, an individual sardine that slips slightly out of alignment, catching the sunlight at the wrong angle. The predator's brain does not deliberate in any human sense. It does not weigh options or ponder strategies. It is a biological targeting computer. It calculates the exact trajectory based on the vector and velocity of the shifting prey, solving complex interception geometry through deeply ingrained neural circuits that have been honed by millions of years of ruthless repetition. When the propulsion finally engages, it is catastrophic. The massive caudal fin, the tail, snaps in a rapid, violent oscillation, and the barracuda's entire body stiffens into a solid, living spear. Water physically shears along its flanks as the fish accelerates from zero to lethal velocity in the blink of an eye, completely exploiting the inertial advantage of its own mass and momentum. For the prey, there is no gradual escalation of terror. There is no drawn-out chase to nervously interpret, no looming shadow to outswim. The very first sensory cue the sardine receives is often the physical displacement of water. the bow wave generated by the predator's incoming mass. But by the time that pressure wave is felt, it is already too late. Survival for a small fish relies entirely on the startle reflex. Embedded deep within their brainstem are specialized, giant nerve cells known as Mothner cells. When a lateral line running down the side of the fish detects a sudden, dangerous change in water pressure, these cells fire, sending an emergency electrochemical signal straight to the spinal cord, triggering an explosive contraction of the muscles on the opposite side of the body. This forces the fish to violently curve into a C shape and rocket away from a threat. It is one of the fastest neural reflexes in the entire animal kingdom, operating in mere milliseconds. But the barracuda's evolutionary masterpiece is that it simply moves faster than the electrochemical signal of fear. The predator's velocity actually outpaces the prey's neurological threshold. The impact occurs before the Mothner cells can complete their circuit. The fish does not experience the sudden shock of impact, the pain of the teeth, or the terror of being eaten. The strike is so instantaneous that the fish's life ends before its brain can even register that the environment has changed. The fear, in biological terms, is the absolute impossibility of preemptive avoidance. You cannot outrun a threat that you cannot perceive. Yet, the complex ecosystem surrounding this violent interaction heavily complicates the narrative. Sardines and other schooling fish are not completely naive victims endlessly drifting in ignorance. The act of schooling itself is a highly evolved, sophisticated response to exactly this kind of intense predation pressure. By aligning their bodies so closely and maintaining such tight, mathematically precise spacing, the individuals actively reduce their per capita risk. They create a massive confusion effect. A predator looking at a tightly packed mass of 10,000 identical, shimmering shapes struggles immensely to isolate and lock onto a single, definable trajectory. In theory, the school functions as a massive, living shield of mirrored light. The barracuda, however, understands the geometry of the school. It does not plunge blindly into the densest, most chaotic core of the bait ball. Doing so would risk missing entirely or colliding awkwardly with hundreds of small bodies, ruining its momentum. Instead, it targets the extreme periphery. It hunts the edges where alignment naturally falters. The fish on the absolute margin of the school carries a wildly disproportionate amount of the risk. This brutal reality drives a constant, desperate internal competition within the shoal. Every single sardine is constantly attempting to push deeper into the center, producing a dynamic, rolling flux of bodies that appears incredibly smooth and hypnotic from a distance, but is internally frantic and intensely competitive. The barracuda simply leverages that desperation. Hydrodynamics play a terrifying role in the aftermath of the initial strike. When a heavily muscled barracuda accelerates to top speed, it pushes a massive bow wave of water ahead of it. As it punches through the edge of the school, this invisible wall of pressure physically disrupts the delicate cohesion of the shoal. The fish nearest to the impact zone are violently scattered, tumbling reflexively and creating momentary gaps in the formation. These sudden gaps amplify the vulnerability of the entire group. In the ensuing chaos of dispersal, a second strike inevitably follows. The barracuda does not rely solely on the element of surprise. It actively capitalizes on the physical fragmentation its speed creates. It slashes through the broken ranks, turning back with terrifying agility to snap up the injured, disoriented fish left spinning in its wake. Therefore, the barracuda's legendary stillness before the attack is not passivity. It is a highly active, heavily armed strategy. By minimizing its physical motion before the strike, the barracuda drastically reduces its probability of being detected. Many prey species rely almost entirely on relative motion against a static background to identify threats. A completely stationary predator seamlessly blends into the visual field. This is aided by the barracuda's brilliant counter shading, dark, steely blue or gray on the top to match the deep ocean below, and pale, shimmering silver on the belly to blend with the bright sunlight filtering down from the surface. The extreme brightness of the open ocean actively compresses color, rendering a hovering barracuda practically invisible until the exact millisecond it decides to move. And yet, here lies the great, underlying reversal of the barracuda's existence. Its absolute reliance on explosive, blinding speed imposes a massive, life-threatening metabolic cost. Those pale, Fast-twitch muscle fibers that generate such terrifying bursts of kinetic power come with a heavy physiological tax. They operate anaerobically, meaning they burn through energy without using oxygen, which rapidly produces massive amounts of lactic acid. After a high-speed sprint, a barracuda is heavily fatigued. Its muscles burn. It is temporarily exhausted. A failed strike is not just a missed meal. It is a critical loss of vital energy that demands a significant recovery period. Repeated misses can utterly deplete the barracuda's energy reserves, leaving it weakened in nutrient-variable waters where the next meal is never guaranteed. Unlike the bluefin tuna, whose red muscle can sustain endless cruising, the barracuda is a slave to ambush efficiency. Precision is not optional. It is mandatory for survival. The prey, over millions of years, have learned to exploit this critical limitation. When faced with a sprinting predator, some prey species abandon uniform schooling and adopt wildly erratic, unpredictable swimming patterns, violently zigzagging to reduce the predictability of their trajectory. Others flee towards structurally complex habitats, massive coral heads, dense mangrove roots, or sunken debris. In these environments, the barracuda's greatest asset instantly becomes its most fatal liability: its rigid, elongated body. Perfectly optimized for straight-line, open-water acceleration, it is terrible at turning sharply. Attempting a high-speed strike inside a dense coral reef is a suicide mission. The predator cannot maneuver fast enough and risks a catastrophic, bone-shattering collision with the limestone. Furthermore, the barracuda is not the undisputed king of the reef. Larger, far more massive predators constantly lurk just beyond this high-speed exchange. Massive bull sharks, tiger sharks, and giant groupers view barracudas not just as competitors, but as highly prized prey. In the bright, open water, the violent, flashing silver explosion of a barracuda strike acts as a massive visual and acoustic beacon. It attracts immediate, unwanted attention. A barracuda completely fixated on slicing through a school of sardines, its muscles burning with lactic acid from the sprint, may suddenly find itself in the jaws of a predator twice its size. The hierarchy of the ocean is intensely fluid, and the blinding speed that terrifies the sardines is not a universal guarantee of dominance. Still, out in the open blue, where the physical structure of the reef fades away and the massive schools of baitfish shimmer like pools of liquid metal, the barracuda's brutal method reigns supreme. It is a realm defined by the terrifying moment before reaction. The prey drift within a delicate illusion of safety, sustained only by their collective vigilance. The predator waits, perfectly still, its fast-twitch muscles tightly coiled beneath a skin that perfectly reflects the ambient light. Then physics intervenes. To accelerate so violently in water requires overcoming immense drag, a resistance that increases proportionally to the square of the velocity. The barracuda achieves this impossible math through its powerful caudal peduncle and a hyper-streamlined profile that absolutely minimizes turbulence. Its scales lie perfectly flat, seamlessly integrated into its skin to reduce any disruption to the boundary layer of water slipping over its body. The first few violent beats of its tail are decisive, generating the exact amount of thrust necessary to completely close the distance before the prey can fully scatter. Its jaws open at the precisely timed millisecond to maximize the gape upon contact. The impact is not always instantly lethal on the very first contact. Those terrifying, serrated teeth are designed to slash. A barracuda will often strike blindly through the densest part of the shoal, tearing and severing prey into smaller, manageable sections rather than swallowing them whole. It will rocket completely through the massive bodies, then wheel sharply around, returning at a slightly slower pace to casually consume the pieces of injured, dying fish trailing in its violent wake. The entire event appears like mindless, chaotic brutality, but it follows highly predictable, deeply ingrained patterns of biomechanics and opportunistic geometry. In the quiet aftermath, the water slowly regains its deceptive stillness. The fragmented shoal frantically reforms, drawing tight once more, closing its ranks as if the violence had never occurred. Evolution demands an incredibly short memory for terror. Constant panic would exhaust their energy reserves and ensure their death. Instead, the surviving fish recalibrate their spacing and quickly resume feeding. The barracuda, having completely expended its explosive burst, glides slowly away, returning to hovering, invisible vigilance. Its rigid muscles slowly relax. Its respiration steadily increases, pumping water over its gills to clear the heavy lactic acid and resolve the massive oxygen debt incurred during the strike. This exact, violent cycle repeats itself countless times every single day across coral reefs and coastal shells around the world. Through this relentless pressure, barracudas actively regulate the populations of mid-level fish, directly influencing the grazing pressure on plankton and algae. Their terrifying presence dictates the very shape and movement of the massive schools, which in turn heavily affects how nutrients are distributed across the ecosystem. That single, blinding strike ripples outward, altering predator-prey dynamics across multiple trophic levels. What truly distinguishes a barracuda is not its brutality, nor its teeth, nor its size. It is its absolute mastery of temporal compression. It condenses the entire act of predation into an instant so inconceivably brief that biological cognition actually lags behind the physical consequence. The prey in these waters are forced to live in a state of perpetual, edge-of-the-knife potential impact. Their tiny neural circuits are hyper-tuned for detection, yet they are perpetually, hopelessly racing against a predator that has evolved specifically to outrun thought itself. The ocean's calm, glittering facade completely masks these violent fractions of a second. The sunlight dances on the waves, the currents drift lazily, and the massive schools glide in hypnotic, beautiful unison. Yet somewhere within that perfect serenity, a predator holds its position, perfectly aligned with the unforgiving physics of speed. There will be no warning call. There will be no shifting shadow to interpret in time. There will only be the sudden, explosive rupture of the water, the vanishing of one silver body, and then, once more, the terrifying return to total stillness. The shell does not crack slowly. It does not yield under a gradual, escalating pressure. It simply detonates. Down in the complex, shifting architecture of the coral reef, a crab edges out from beneath a limestone ledge. Its stalked eyes pivot, scanning the immediate vicinity, while its delicate antennae whip back and forth, probing the water for the microscopic chemical traces of decaying organic matter. Its heavy, armored claws are held half-raised, locked in a state of habitual, instinctual caution. To the crab's highly attuned sensory apparatus, the environment is completely neutral. There is no looming shadow approaching from above. There is no sudden, alarming shift in the water current. There is absolutely no prolonged, mounting tension that might signal an impending attack. The water is heavy, warm, and perfectly still. And then, a blinding blur of kaleidoscopic color flashes from a tiny, dark crevice in the rock. Before the crab's neural circuitry can even begin to translate that visual stimulus into a muscular command for movement, the entire world simply fractures. It shatters in a terrifying burst of cavitation bubbles and pulverized calcium carbonate. The mantis shrimp does not chase its prey. It does not stalk across the open, exposed sand with drawn-out, menacing patience like a predatory cat. It waits inside a perfectly carved burrow, a dark tunnel hollowed out of the reef rock or packed sediment. Inside this narrow fortress, its forelimbs are folded tightly against its body, completely locked in place like the heavy, steel arms of a loaded bear trap. These raptorial appendages, which, depending on the specific species, are highly modified into either heavily weighted, hammer-like clubs or serrated, spear-like blades, are held under agonizing, immense tension. This tension is not maintained by mere muscle power. It is regulated by a highly complex biological latch mechanism. Energy is slowly, methodically accumulated and stored within highly specialized, saddle-shaped cuticular structures in the arm, which act as organic springs. The predator is not poised for a gradual escalation of force. It is, quite literally, coiled physics. As the crab inches closer to the dark entrance of the burrow, it remains blissfully unaware that proximity is the only variable required for a total catastrophe. It does not know it has crossed an invisible, lethal threshold. To understand the absolute terror of this ambush, you must understand the eyes of the creature waiting in the dark. Mantis shrimp possess arguably the most complex, incomprehensible visual systems in the entire animal kingdom. While humans navigate the world using 3 types of color-receptive cones, the mantis shrimp possesses up to 16. Their independently moving eyes can detect polarized light, circularly polarized light, and a massive spectrum of wavelengths spanning from deep ultraviolet to far infrared. Each individual eye possesses trinocular vision, meaning a single eye can gauge depth and distance with flawless mathematical precision. Yet, this staggering, almost alien-level perception is not deployed to appreciate the beauty of the reef, nor is it used to track prey across vast, open distances. It is used exclusively as a close-range targeting computer. The Mantis Shrimp calculates angle, distance, and optimal striking geometry within a confined visual field measured only in centimeters. It is waiting for the exact, perfect millimeter of alignment. When the crab finally steps into that millimeter, the latch releases. The heavily armored club accelerates forward with a velocity that defies biological sense. It moves so fast that it reaches speeds comparable to a bullet, leaving the barrel of a .22 caliber rifle. This astonishing acceleration generates kinetic forces entirely sufficient to instantly fracture dense mollusk shells, shatter thick crustacean exoskeletons, and completely destroy the defensive architectures that took millions of years to evolve. But the physical impact of the club is only half of the violence. The strike is so unfathomably rapid that it physically tears the water apart. As the club rockets forward, the water simply cannot move out of the way fast enough. The pressure drops so dramatically behind a moving limb that the water literally boils at room temperature, creating empty cavities in the fluid known as cavitation bubbles. When these vapor bubbles immediately and violently collapse in on themselves, they unleash a terrifying secondary shock wave. The implosion is so intense that it generates a microscopic flash of light, a phenomenon known as sonoluminescence, and temperatures inside the collapsing bubble briefly reach thousands of degrees, rivaling the surface of the sun. If the initial bone-shattering physical blow of the club somehow misses the crab by a fraction of a millimeter, the resulting shock wave from the collapsing cavitation bubbles is often enough to stun, dismember, or outright kill the prey anyway. The crab does not experience a logical sequence of threat, followed by impact, followed by pain. It experiences an instantaneous, total collapse of its physical structure. This is not merely a heavy mechanical blow. It is a biochemical and neurological event compressed into microseconds. The Mantis Shrimp strike completely and utterly outpaces the prey's startle reflex. The neural pathway in a crab or a fish is evolved to trigger a rapid, life-saving escape in response to sudden, dangerous stimulus. But the inherent latency in synaptic transmission, the actual time it takes for an electrical signal to travel from the eye to the brain and down into the muscles, though measured in incredibly brief milliseconds, is simply too slow. By the time the ion channels in the crab's nerves open and the muscles finally receive the frantic signal to contract and flee, the club is already connected, the shock wave has already detonated, and the exoskeleton has already failed. The true terror here lies entirely in temporal compression. There is no escalating arc of fear. There is no desperate, lung-burning sprint through narrowing corridors of coral. The precise moment of contact is absolutely indistinguishable from the very end of life. To wield such devastating power, the Mantis Shrimp embodies a fascinating, evolutionary paradox of extreme fragility and overwhelming force. Their bodies are relatively small, long, and soft, often completely concealed within their narrow burrows because they severely limit mobility. A Mantis Shrimp cannot pursue fleeing prey across the open terrain. They possess absolutely no aerobic endurance. Instead, evolution has invested every ounce of their biological capital into that latch-mediated spring mechanism. This mechanism perfectly exemplifies a brutal physical principle known as power amplification. Energy is stored incredibly slowly, muscle fibers contracting fraction by fraction over a long period of time, packing potential energy into the organic spring. Then, all of that stored energy is unleashed in a fraction of that duration. The predator completely trades stamina and mobility for one instance of absolute, instantaneous, localized dominance. The crab's heavy shell, composed of tough chitin intricately reinforced with crystallized calcium carbonate, is beautifully designed to withstand the steady, crushing pressure of a fish's jaw or the minor, chaotic impacts of the tumbling surf. It is not, however, optimized for a high-velocity, ballistic shock delivered at a precise, calculated angle. But how does the Mantis Shrimp survive its own weapon? Striking an armored crab with the force of a bullet should logically shatter the predator's own arm into pieces. The secret lies in the microscopic architecture of club itself. It is structured with an incredibly complex, layered composition of hydroxyapatite, the same mineral found in human bones and teeth, arranged in a unique, spiraling herringbone pattern. This microscopic shock absorber brilliantly dissipates the immense stress of the impact, actively preventing microscopic cracks from expanding and causing self-damage. Specialized, softer regions within the club absorb and effortlessly redistribute the rebounding force, allowing the predator to deliver devastating blow after devastating blow, day after day, without ever suffering a structural failure. In the immediate aftermath of the strike, fragments of shattered shell and clouded tissue drift slowly through the water column. The mantis shrimp retreats slightly back into the shadows of its burrow, waiting for the dust to settle, and then carefully advances to drag the incapacitated, broken prey inside. Feeding occurs methodically, quietly, in the dark, but the decisive, terrifying event has already passed into history. The burrow entrance returns to its deceptive stillness, its brightly colored occupant silently resetting the internal biological latch, coiling the springs for the next inevitable encounter. Ecologically, the presence of the mantis shrimp exerts a massive, unseen selective pressure on the populations of hard-shelled invertebrates. They act as the apex regulators of the microscopic benthic world, heavily influencing the population dynamics of crabs, predatory snails, and burrowing bivalves across entire reef systems. Their terrifying presence literally shapes the physical distribution of prey species, who will actively avoid substrates heavily populated with mantis shrimp burrows, altering their foraging patterns and daily migrations to minimize their exposure to the invisible snipers. In this way, the instantaneous microscopic strike of a single shrimp reverberates outward in massive waves, dictating the behavioral adaptations of the entire benthic community. Yet, the narrative of this incredible creature does not remain one of unilateral, undisputed invincibility. The mantis shrimp is itself highly vulnerable to larger, roaming predators such as triggerfish, groupers, and particularly octopuses. Outside protective, heavily fortified radius of their limestone burrows, their long, soft bodies offer almost zero defense. Their total reliance on extreme, close-range proximity means that any exposure in the open water carries a massive, life-threatening risk. The exact same hyperspecialization that grants them their unmatched, ballistic striking speed permanently confines them to a microscopic territory measured only in meters rather than miles. Furthermore, their burrow represents a deadly dual reality. It is both an impenetrable fortress and a potential tomb. If the surrounding sediment shifts in a storm, or if a piece of heavy coral rubble collapses, their narrow escape routes may be permanently blocked. In reef habitats that are heavily disturbed by human activity or extreme weather, burrow stability drastically declines, skyrocketing their mortality risk. The ultimate predator of the microsecond is hopelessly, utterly dependent on geological patience and structural stability. There is also an incredibly unexpected, almost poetic dimension to their visual sophistication. While the mantis shrimp possesses a staggering, unmatched diversity of photoreceptors, advanced neurological research suggests that their tiny brains may actually process and categorize colors entirely differently than human perception does. Rather than blending colors to see millions of nuanced shades, they likely use their 16 cones as a rapid-fire scanner, prioritizing the absolute, fastest possible discrimination of specific light signatures over detailed, contemplative comparison. Their magnificent, alien eyes are optimized entirely for the sheer speed of recognition. Vision, for the mantis shrimp, does not serve aesthetic appreciation or the enjoyment of the reef's beauty. Vision serves the strike, and the evolutionary reversal deepens even further when considering their social lives. The mantis shrimp's terrifying, ballistic ferocity completely masks a life defined, for many species, by long-term territorial solitude and surprising tenderness. Many species of mantis shrimp are strictly monogamous. They form incredibly strong, lifelong pair bonds, living together, sharing a single burrow and raising their young in tandem for decades. The lethal, bone-shattering club is wielded fiercely against prey and occasionally in offense against larger predators, but is also used in highly ritualized heavily moderated combat with rival Mantis Shrimp over territory. Yet, these intense confrontations are governed by complex signaling, threat displays, and calculated assessments, specifically evolved to minimize fatal outcomes. They punch each other's heavily armored tail sections, testing strength without causing death. Their violence is extraordinarily precise. It is never indiscriminate, returning to the exact moment of impact at the mouth of the burrow. The defining, inescapable feature of the predation is the absolute absence of transition. The crab does not sense an encroaching, looming danger over a long distance. It does not feel the water chill or the shadows lengthen. It simply crosses an invisible mathematical threshold in the sand, and it is instantly erased by the laws of physics. The water's surface above remains utterly undisturbed. No massive, dark predator arcs dramatically through the blue water. The entire catastrophic event is completely confined to a space barely larger than the predator's own tightly coiled body. In a massive, sprawling reef ecosystem that is so frequently defined by prolonged, exhausting chases, coordinated pack hunting, and slow, agonizing constriction, the mantis shrimp represents an entirely different axis of fear. It compresses the very concept of cause and consequence into a single, blinding flash. The environment does not gradually constrict around the prey. It does not surround or outlast them. It simply converts from completely neutral to absolutely lethal without a single perceptible warning. After the feed, the burrow mouth, dark and entirely unassuming, resumes its role as a simple architectural feature of the rock rather than an active, loaded threat. Small, colorful reef fish and scavenging crustaceans resume their daily, oblivious foraging, navigating the sprawling mosaic of rock and sand. Yet, hidden just millimeters within that narrow, silent cavity lies a biological mechanism capable of delivering kinetic force comparable to a military projectile. The mantis shrimp waits. It's heavy. Armored appendages are tightly folded. Biological energy is slowly, methodically accumulating within the elastic structures of its arms. The dense muscles contract over time, without producing a single millimeter of visible movement, silently storing lethal potential. Time stretches infinitely in the dark stillness until proximity perfectly aligns with calculation. Then, in a fraction of a millisecond completely beyond the limits of perception, that stored energy becomes a devastating impact. And for the prey wandering just a fraction too close, the exact moment of contact is absolutely indistinguishable from the end of the world. The reef does not lunge. It does not chase. It inhales. A juvenile wrasse drifts lazily through the sun-dappled shallows, its body flickering with cautious, ever-present curiosity. It is searching for microscopic plankton suspended in the water column, navigating a complex, three-dimensional mosaic of branching corals, shifting shadows, and encrusted limestone. The tiny fish is acutely aware of its surroundings, its lateral line constantly reading the water for the pressure waves of an approaching predator, its eyes scanning for the telltale silhouettes of groupers or snappers. But right now, the ocean feels calm. Nothing is moving. Directly ahead of the wrasse lies a seemingly innocuous mound of rubble, heavily encrusted with a thick, textured layer of dull orange sponge and swaying algae. Nothing moves, except for one microscopic detail. A tiny, worm-like filament twitches lazily just above the surface of the sponge. The wrasse, entirely driven by millions of years of foraging instinct, angles closer. Its visual system is exquisitely tuned to detect exactly this kind of prey-sized motion against a highly complex, chaotic background of the reef. It locks onto the twitching filament. The wrasse is not approaching a predator. In its mind, it is approaching a guaranteed opportunity. It closes the distance, entirely unaware that the rock it is swimming toward is breathing. In less time than a nerve impulse can physically travel from the wrasse's eye to its brain, the entire reality of the ocean violently rearranges itself. The piece of encrusted rubble suddenly becomes a cavernous mouth. The surrounding water instantly becomes a massive, inescapable vacuum. And the juvenile wrasse is simply no longer a part of the scene. The frogfish does not hunt in any conventional sense of the word. It does not stalk its prey through the coral corridors, nor does it rely on the blinding, straight-line acceleration of a barracuda. Instead, it waits. It exists as a piece of the reef itself. It performs a biological impersonation so deeply absolute so flawlessly executed that the very boundary separating predator from substrate completely dissolves. To look at a frogfish is to look at an evolutionary masterpiece disguised as a biological mistake. Its skin is not smooth and streamlined like a pelagic hunter. It is heavily textured, covered in bizarre dermal spinules, fleshy warts, and irregular, ragged flaps of tissue that perfectly mimic the jagged edges of dead coral, toxic sponges, or waving fronds of algae. This is not a static disguise. Over the span of days, the frogfish painstakingly re-engineers its own cellular appearance. Its pigmentation slowly shifts, regulated by highly sensitive chromatophores that constantly respond to the visual cues of its immediate environment, perfectly matching the exact color gradients of the rock it sits upon. The frogfish is the ultimate embodiment of environmental noise. It does not just hide, it forces the prey's brain to actively ignore it. But perfect camouflage is entirely useless if the prey never comes within striking distance. What ultimately betrays the frogfish's terrifying presence is the lure. Protruding from the top of its head is the elysium, a highly modified, elongated dorsal spine that arches forward like a fisherman's rod. Terminating at the very end of the spine is a fleshy, bait-like appendage known as the esca. The frogfish moves this appendage with mesmerizing, subtle precision, perfectly mimicking the erratic, jerky twitch of a dying worm or struggling shrimp. It casts its line directly into the visual blind spots of the passing fish. While the lure dances, the frogfish's massive, misshapen body remains in a state of terrifying, absolute stillness. This immobility is not a lack of action. It is a fundamental architecture of its entire strategy. Unlike pursuit predators that must rely on massive muscular bursts across open distances, frogfish are built from the ground up for one thing: an explosive, reality-bending suction event within a microscopically confined radius. Their physical anatomy is bizarre. Their pectoral fins do not function like the hydrofoils of a shark or the paddles of a turtle. They function exactly like thick, stubby hands. The frogfish uses these modified limbs to physically grip the rock, allowing it to slowly, incrementally walk across the substrate or securely anchor itself against the pulling currents. It locks itself down, bracing for the massive physical recoil of its own weapon. That weapon lies entirely within its cranial mechanics. The skull of a frogfish is not a solid, rigid helmet. It is a highly complex, loosely articulated framework held together by incredibly elastic ligaments. This specialized anatomy permits an extraordinary, almost grotesque expansion of the buccal cavity, its mouth and throat. When the strike finally comes, it is not a bite. Biting implies that the predator moves forward to close its jaws around a target. The frogfish does not move forward. It causes the space around the prey to violently collapse inward. The wrasse moves within range, entirely unaware that physical proximity is the final, fatal variable required to trigger the trap. The frogfish's mouth suddenly opens with a speed that defies physical logic, expanding its internal volume to as much as 12 times its resting size in a fraction of a millisecond. Massive opercular flaps on the sides of its head swing violently outward, and the entire buccal cavity inflates like a rapidly expanding balloon. This instantaneous expansion creates a massive, sudden negative pressure gradient. The water directly in front of the frogfish, along with the terrified wrasse suspended within it, is violently drawn inward. The sheer force of the suction event is so rapid that standard video cannot capture it. High speed, scientific imaging reveals that the entire sequence, from the opening of the jaws to the closing of the trap, unfolds in as little as 6 milliseconds. It happens significantly faster than the prey species can even initiate a startle response. Just like the sardine facing the barracuda, the wrasse is equipped with specialized Mothner neurons in its brainstem designed to trigger a life-saving, explosive escape at the first sign of danger. But the latency of neural conduction, the time it takes for the fish to literally realize it is dying, is measured in tens of milliseconds. The frogfish operates comfortably within that delay. It actively outpaces the biological circuitry designed to save the prey's life. The environment changes not through a visible incoming attack, but through an instantaneous hydrodynamic reversal. The very water that once calmly supported the wrasse instantly becomes a violent, unstoppable force pulling it forward into the dark. Inside the cavernous, expanding mouth, rows of sharp, inward-pointing teeth ensure that once the prey crosses a threshold, it is fully secured. The massive jaws snap shut and the trap is sealed. Frogfish are capable of swallowing prey nearly the exact same size as their own bodies. This impossible feat is facilitated by incredibly distensible, highly elastic stomach walls capable of stretching to accommodate massive, struggling meals. After the ingestion is complete, the predator does not go looking for dessert. It may remain completely motionless in that exact same spot on the reef for days, sometimes weeks, slowly metabolizing its massive catch and conserving every ounce of its energy. Its hunting strategy is entirely defined not by frequency or endurance, but by ruthless, unmatched efficiency. The profound terror of this encounter lies in the concept of transformation. What appeared completely inert suddenly becomes violently animate. What seemed fundamentally harmless becomes instantly lethal. The wrasse did not die because it failed to flee a pursuer. It died because it confidently approached the facade. From a broader ecological perspective, frogfish occupy a highly specialized niche of ambush predation that exerts a massive, silent selective pressure on the vigilance of the entire reef. Every single reef fish must constantly, endlessly balance the desperate need to feed against a rigorous life or death risk assessment. Overreacting to every single piece of jagged rubble or swaying sponge would completely squander their energy and rob them of feeding opportunities. They would simply starve to death out of pure paranoia. But underreacting, even for a millisecond, invites absolute catastrophe. The frogfish perfectly exploits this terrifying evolutionary trade-off. It actively inserts itself into the sensory blind spots of prey decision-making, and its camouflage is not purely visual. By remaining absolutely motionless and perfectly matching the physical texture of surrounding substrate, the frogfish becomes entirely invisible to the lateral line systems of other fish, which sense changes in water pressure. In a dynamic reef environment where currents constantly shift and particles drift, the complete absence of hydrodynamic turbulence around a frogfish fundamentally reinforces its deadly disguise. It is not merely unseen by the passing fish. It is entirely unremarkable. Yet, deeply embedded within this apparent, localized dominance lies a profound, evolutionary vulnerability. The frogfish has traded everything for its strike. They are exceptionally poor swimmers, entirely lacking the sleek, streamlined bodies of pelagic hunters. Their locomotion is hilariously awkward, a series of clumsy, short hops propelled by those modified, hand-like fins. If a frogfish is somehow forced into the open water, stripped of its textured background, it is overwhelmingly conspicuous and agonizingly slow. It becomes a sitting duck. Larger, roaming predators such as massive groupers or moray eels will readily consume them if they are discovered out of place. Their entire existence, their absolute reliance on deception, demands suitable habitat. Without a complex, textured substrate to blend into, their grand illusion instantly fails. The narrative reversal deepens dramatically when considering that the frogfish's bizarre, grotesque appearance, which is so easily perceived as a massive weakness in a harsh marine world that generally favors blinding speed and sleek grace, is, in actual fact, the absolute pinnacle of evolutionary specialization. Its ungainly, lumpy body is a massive evolutionary investment in pure suction mechanics and flawless disguise. The very traits that utterly limit its mobility are the exact same traits that enable the instantaneous, reality-bending expansion that defines its lethal strike. Even more intriguing is a frogfish's silent, outsized role within the trophic dynamics of the entire coral reef. By aggressively preying on the small, herbivorous fish that constantly graze on algae or the tiny wrasses that consume invertebrates, the frogfish indirectly but heavily influences the overall health of the coral and the intense competition among reef organisms. A single, successful ambush by a hidden frogfish sends microscopic ripples outward, slightly altering the delicate, ongoing war between aggressive algae expansion and slow coral growth. The trap extends far beyond the individual prey. It reaches into the subtle, shifting balance of the entire ecosystem. The frogfish's strike is universally recognized as one of the fastest feeding events among all vertebrates on the planet, but sheer speed alone does not define its terrifying impact. It is a jarring, violent juxtaposition of absolute stillness and explosive expansion. It is a sudden conversion of apparent, boring safety into an instantaneous void. Prey species may swim past the exact same piece of sponge dozens of times, becoming completely habituated to the predator's presence, writing it off as mere background architecture. Then, in one fatal moment of perfect alignment between the twitching lure, the exact distance, and the prey's divided attention, the entire reef physically rearranges itself. The local populations of wrasse and damselfish learn, but they only learn through brutal, unforgiving attrition. The individuals that are naturally predisposed to approach certain textures too closely, or those that respond far too eagerly to isolated, twitching movements, are rapidly and violently removed from the gene pool. Over generations, the behavioral biases of the prey subtly shift, favoring a slightly increased, paranoid caution around any ambiguous stimuli. But the frogfish adapts in kind. It alters its coloration over days, slowly shifting its patterns and constantly refining the motion of its lure to perfectly match the prevailing expectations of its prey. It is an endless, high-stakes evolutionary dialogue conducted in absolute silence. Within the overwhelming, chaotic complexity of the coral reef, the frogfish stands as a living paradox. It weaponizes immobility. It does not vigorously patrol a marked territory, and it absolutely never chases fleeing schools of fish. It simply becomes a seamless part of the habitat, until the exact moment the habitat violently betrays those who foolishly place their trust in it. Its cavernous mouth, capable of engulfing life with virtually zero warning, is less a traditional biological weapon than it is a localized vacuum that completely erases physical distance. And when the lightning-fast strike concludes, the environment immediately appears utterly unchanged. The water settles in an instant. The jagged rubble remains exactly where it was. The ore and sponge sways gently in the invisible current. Only the sudden, total absence of small fish marks the violence of the event. The predator slowly settles its massive stomach, relaxing its elastic ligaments back into their hidden folds, and descends back into perfect, terrifying stillness. The Elysium is raised, the fleshy lures extended once more, twitching lazily in the current, patiently waiting for another curious, fatal approach. In the dark, specialized domain of the frogfish, fear is entirely retrospective. It is the dawning, horrific comprehension that occurs only inside the dark, crushing confines of the predator's stomach. Had there been even a millisecond of time to comprehend it, the prey would have realized that their feeling of safety was nothing more than an elaborate illusion, meticulously crafted from texture, color, and infinite patience. The trap was always present. It was heavily embedded in plain sight. But by the time recognition finally occurs, recognition no longer matters. The seal never sees the lethal geometry forming in the dark waters beneath it. At the exact boundary where the ocean meets the sky, the world feels incredibly open, expansive, and almost buoyant with safety. The harsh, brilliant sunlight fractures into thousands of shimmering silver ribbons, scattering playfully across the seal's whiskered face as it breaks the surface, exhaling in a quiet, misty plume before rolling gently back into the cold water. Above the animal, the sky is an infinite, pale dome of safety. But directly below, the ocean rapidly collapses into an impenetrable, crushing ink. The seal's heavily muscled body moves with an easy, fluid confidence, its four powerful flippers slicing cleanly and efficiently through the thin, upper layer of the sea where the sunlight still manages to penetrate. But beneath that fragile, illuminated threshold, down where the bright blue rapidly fades into a pressure-darkened void, an entirely different, terrifying calculus is silently unfolding. The predator waiting in the deep is not rushing. It is not engaged in a frantic, exhausting chase. It is calculating. The seal's exact silhouette has already been meticulously measured. Its swimming trajectory has been precisely plotted against the unforgiving physics of buoyancy, water resistance, and light refraction. The beautifully calm, glittering surface of the ocean is nothing more than a lethal illusion born of ignorance. The hunt has actually begun long before the seal feels anything at all. Seals are incredibly advanced marine mammals, beautifully evolved over millions of years to completely master the boundary layer, that thin, luminous interface between the air and the sea where a vital breath can be taken and the light can still be easily read. Their large, forward-facing eyes are exquisitely adapted to gather even the faintest traces of illumination. Their retina is densely packed with specialized rod cells to drastically enhance their visual sensitivity in the dim, murky water. Their vibrissae, those thick, highly innervated tactile whiskers protruding from their muzzles, are biological marvels. They can physically detect a minute microscopic hydrodynamic trails left behind by passing fish, reading the invisible turbulence patterns in the water with absolute neurological precision. Every single anatomical feature of the seal suggests a state of hyper-awareness. Yet, the fundamental architecture vision in the open ocean is brutally, fatally asymmetric. From the seal's perspective looking down, the ocean surface reflects and refracts the ambient light, scattering the incoming solar rays into unpredictable, chaotic angles that completely obscure whatever lies in the deep. The water hides its own interior, but from the perspective of the predator looking up, the exact opposite is true. From the deep, the ocean surface becomes a brilliant, luminous ceiling. Any creature, no matter how stealthy or perfectly camouflaged, that swims near that glowing lid is instantly rendered as a stark, high-contrast silhouette against the blinding brightness of the sun. The predator lurking below sees a dark, impossibly crisp outline. The seal looking down sees only a bottomless, empty void. This visual imbalance is not an incidental quirk of nature. It is a fundamental, structural optical trap perfectly engineered by the physics of the sea. Water naturally absorbs the longer wavelengths of light first, rapidly swallowing the vibrant reds, oranges, and yellows as the depth increases, leaving only a rapidly narrowing, cold spectrum of deep blue. As the light steadily diminishes, three-dimensional shapes begin to flatten out. They lose their depth and detail, becoming pure silhouettes. A seal casually cruising within the top few meters of the water column instantly becomes a glowing, high-contrast cutout moving across the sunlit lid of the world. Beneath that brilliant lid, the predator's vision violently sharpens. It is actively tuned by evolution for contrast detection rather than fine, aesthetic detail recognition. The great white shark or the massive, transient orca does not need to see the color of the seal's fur or the exact nuance of its movement. It only needs outline. It only needs motion. And by simply existing at the surface, the seal provides both in perfect clarity. But the true terror of this encounter is never found in the violent strike itself. The terror is in the waiting. Apex predators that specialize in attacking from the crushing depths do not rely solely on the brute force of their upward acceleration. They rely on a masterful layering of overlapping sensory systems. Embedded deeply within the snout of a great white shark are specialized, gel-filled pores known as the ampullae of Lorenzini. These microscopic receptors are so unfathomably sensitive that they can detect the unimaginably faint microvolt electrical fields generated by the simple, involuntary muscle contractions of a living animal. As the seal's heart beats, as its diaphragm flexes to breathe, it broadcasts an electrical beacon into the salt water. Simultaneously, the predator's lateral line system, a network of hypersensitive mechanoreceptors running along its flanks, registers a minute, rhythmic pressure waves cascading through the water as the seal's flippers beat back and forth. Deep within the shark's nasal cavities, highly advanced olfactory tissues furiously analyze microscopic, dissolved traces of scent, reading biological signatures carried across deep, cold currents that are completely invisible to the seal above. By the exact moment the predator finally decides to angle its massive body upward and begin its lethal ascent, the seal has already been perfectly mapped in multiple, overlapping sensory dimensions. The violent, explosive attack is merely the final, inevitable physical expression of a cold, calculated process that actually began several minutes earlier. In this moment, the narrative seems incredibly simple. The seal is merely prey. It is hopelessly vulnerable at the surface, utterly betrayed by the unforgiving laws of physics and the treacherous nature of light. But that simple assumption fractures the moment it is placed under serious biological scrutiny. For the seal's apparent foolish exposure to the surface is actually a highly calculated life-or-death trade-off, entirely shaped by harsh metabolic constraints and the unforgiving economics of oxygen. Diving deep into the pitch-black darkness would absolutely not eliminate the seal's risk. It would simply introduce an entirely different set of horrors, a different cast of predators, and a completely different set of environmental hazards. Depth drastically increases physical pressure, dangerously compressing the air spaces within the seal's body and rapidly accelerating the depletion of its precious oxygen reserves. Seals manage their breath with staggering, almost supernatural physiological control. When they dive, they deliberately shunt their blood flow away from their extremities, directing it only to their most essential organs. They artificially slow their own heart rates down to a few agonizing beats per minute, in a state known as profound bradycardia. Yet, even with these miraculous adaptations, extended deep dives demand an inevitable, heavy toll. They require prolonged recovery time at the surface. Lingering in the boundary layer is not an act of carelessness or recklessness. It is an absolute, unavoidable biological necessity. And out of that dire necessity, extreme adaptation is bred. The seal's body is spectacularly built for a sudden, violent vertical displacement. Its flexible spine can snap and flex with explosive, whipping force. Its highly developed rear flippers are capable of generating an amount of forward thrust entirely sufficient to drastically alter its trajectory in a fraction of a millisecond. Beneath its sleek, hydrodynamically perfect skin lies a thick, heavy layer of blubber. This dense tissue is very often misunderstood and mischaracterized by observers as mere thermal insulation against a freezing water. In biological truth, this adipose tissue is both thermal armor and a massive, highly accessible energy reservoir. It is designed to instantly sustain rapid, violent bursts of anaerobic movement when the body's oxygen runs dangerously low. When the strike finally comes roaring up from the dark abyss below, the seal's survival does not depend on outswimming the massive predator in a prolonged, exhausting marathon. It depends entirely on outmaneuvering the beast in a single, perfectly timed instant. Predators that choose to attack from the deep face a massive, inescapable physiological paradox of their own. To reach the surface quickly enough to catch the seal, they must accelerate upward at maximum velocity, converting their heavily stored muscular energy into sheer vertical speed. But as they ascend, the physics of the ocean begin to actively work against them. As they rush toward the surface, their natural buoyancy rapidly increases. The crushing, deep water pressure that once compressed the gases within their massive bodies suddenly relaxes. They become lighter, they become faster, but they also lose control. Their own massive silhouette becomes entirely visible against the bright ceiling. Once they commit to that explosive, vertical trajectory, they are locked in. The sheer momentum of their massive bodies absolutely limits any last-moment, fine-tuned course corrections. If the shark or the orca miscalculates the seal's exact position by even a single body length, the entire calculated opportunity collapses into a violent, spectacular failure. The seal, constantly hovering in a state of high alert, senses the faintest, almost imperceptible distortion in the water pressure rising from below. Or perhaps its incredibly sensitive eyes detect a sudden, unnatural shift in the light pattern filtering up from the deep. In that microsecond, the seal can twist laterally, violently throwing its body out of the direct line of the predator's aim. The ocean's calm, mirrored surface actively conceals not just the terrible danger of the hunter, but the profound, mutual vulnerability of the hunted. There are extensively documented moments in marine biology where seals have exploited this exact dynamic with astonishing, breathtaking precision, rather than fleeing horizontally across the surface in a blind, terrified panic, which would keep them perfectly silhouetted against the bright sky. Some seals perform abrupt, violent corkscrew dives. They plunge straight downward at impossibly sharp angles, deliberately cutting directly into the massive predator's line of descent, visually breaking their own silhouette and entirely disrupting the hunter's targeting sequence. Others have been observed surging directly toward the massive set of jaws rushing up to meet them, intentionally collapsing the physical distance before the predator's acceleration can reach its lethal peak, effectively forcing a physical misfire. What appears to a human observer on a boat to be blind. Chaotic panic is very often a highly advanced, deeply encoded neuromuscular choreography, perfectly refined over millions of years of evolutionary warfare. The neural pathways linking the seal's sensory input to its immediate motor response are honed to absolutely minimize synaptic delay. In these terrifying fractions of seconds, survival hinges entirely on the literal speed of thought. Yet, even this intense portrayal drastically understates the true ecological complexity playing out beneath the scene. The mere, unseen presence of these massive apex predators heavily influences the behavior of the seal populations long before any individual physical encounter actually occurs. This is the invisible architecture of the trophic cascade. In coastal regions where massive white sharks or transient orcapods are known to patrol frequently, the seals fundamentally alter their entire existence. They change their haul-out patterns on the beaches. They drastically shift their feeding times to avoid peak predator hunting hours. They completely modify their travel corridors, abandoning the most direct, efficient routes in favor of complex, unpredictable paths. They actively cluster near dense, tangled kelp forests or highly complex rocky substrates that physically disrupt and completely negate a deep predator's vertical attack path. The fear itself, the mere psychological pressure of the unseen hunter, reshapes the physical movement of thousands of animals across entire coastal ecosystems. Because the seals refuse to venture into the open water, they drastically reduce their grazing pressure on the local populations of herbivorous fish and invertebrates within the kelp beds. As a direct result, those kelp forests grow denser, larger, and more robust. The unseen predator hiding in the dark does not merely kill the seal. It actively reorganizes the physical structure of the entire ecosystem through the sheer application of psychological terror. And here lies the ultimate, deepest reversal of the narrative. The paralyzing terror of being watched from below is not solely an affliction suffered by the seal. The seal, too, watches the deep. Its large, perfectly adapted eyes constantly scan the dim, impenetrable blue beneath it, effortlessly interpreting microscopic gradients of shadow and subtle shifts in contrast that most terrestrial mammals could never even begin to decipher. Its highly sensitive whiskers extend outward into the water, splayed wide like a living array of advanced antennae, constantly reading the minute, chaotic disturbances in the fluid medium. What seems to us like complete, open vulnerability floating at the surface is, in biological reality, a state of extreme hyper-awareness. The ocean's surface is not a place of ignorance. It is an advanced sensor platform. In the freezing polar waters, where drifting ice flows fracture the sunlight into chaotic, blinding geometries, this deadly interplay becomes even more intensely intricate. Seals resting near breathing holes in the thick sea ice are acutely, intimately aware that massive predators may be waiting in the pitch black directly beneath those very apertures. The breathing hole is both their absolute lifeline and their most lethal trap, but the seals respond with incredible behavioral plasticity. They distribute themselves completely unpredictably across the ice flows, ensuring they minimize the chance of mass displacement if an orca attempts to shatter the ice from below. They maintain constant sentinel vigilance, even while they appear to be deeply asleep. Through a miraculous evolutionary adaptation, they are capable of unihemispheric sleep. One entire half of their brain can enter a deep state of restorative rest, while the other hemisphere remains fully awake, keeping one eye open, constantly scanning the water. It is the ultimate neurological compromise between the desperate need for physical recovery and the absolute requirement for survival. The ocean only looks calm because the physical surface tension of the water smooths out its expression. Beneath that shimmering veneer, the water is fiercely divided by invisible gradients of temperature and salinity, forming massive physical boundaries known as thermoclines and haloclines. Sound travels completely differently across these distinct layers, heavily bending and refracting in ways that can actively mask or suddenly amplify the noise of movement. A massive predator rapidly rising from the cold, dense water of the deep into the warmer, sunlit strata near the surface may briefly, disastrously lose its acoustic clarity. A seal passing rapidly through these same temperature gradients might deliberately distort its own acoustic signature, confusing the hunter below. The battlefield of the open ocean is absolutely never two-dimensional. It is deeply stratified. It is layered. It is intensely dynamic. When a violent breach finally occurs, when a massive predator erupts upward to the surface in a terrifying, spectacular plume of white water and torn, bloody spray, the sheer spectacle instantly captures human attention. But by that exact point, the biological story is already over. The true, terrifying drama unfolded completely in the darkness. It was the silent, mathematical triangulation. It was the microscopic, subtle adjustments in depth. It was the complex metabolic calculations balancing the rapidly depleting oxygen reserves against the fleeting window of opportunity. The seal's fear, if it can even be properly categorized as fear, is deeply embedded not in conscious, anxious anticipation, but an inherited cellular reflex. Thousands of generations of brutal selection pressure have permanently encoded caution directly into their muscle memory. To the casual observer floating safely above on a boat, the sea appears utterly tranquil. The sunlight dances on the swells. The ripples shimmer in the breeze. The seal glides peacefully, its beautifully rounded head breaking the surface in calm, rhythmic intervals to breathe. Nothing seems amiss. Yet, the predator's perspective from the abyss completely inverts that tranquility into a lethal opportunity. The luminous ceiling of the ocean outlines the prey with flawless mathematical clarity. The fragile boundary separating light and dark becomes a fully weaponized horizon. And still, the narrative absolutely refuses to settle into a simple, binary hierarchy of helpless victim and invincible executioner. For apex predators, too, operate within incredibly unforgiving constraints. Missing a strike expends an immense, dangerous amount of energy. Repeated, failed attempts risk absolute starvation. Juvenile sharks and inexperienced orcas must learn the incredibly complex geometry of the vertical ascent through grueling, exhausting trial and error, very often enduring painful, energy-draining miscalculations. In this endless interplay, the seal is never passive. It is a highly active, fully armed participant in an ancient evolutionary arms race that is measured not merely in the sharpness of teeth or the sheer output of speed, but in the micro-adjustments of perception and the absolute perfection of timing. The true, deep terror of being watched from below is therefore not about ignorance. It is about asymmetry. It is the cold, hard realization that in certain layers of the world, the fundamental laws of physics heavily favor one perspective over another. The seal swims smoothly through the blinding brightness, entirely unaware of the precise, exact location of its observer, yet exquisitely, painfully attuned to the absolute possibility of its existence. The predator waits patiently in the freezing shadow, supremely confident in the high contrast of the silhouette, but acutely vulnerable to a single misjudgment in its trajectory. Both creatures are hopelessly bound by the exact same fluid medium. They are bound by the exact same unyielding laws of light absorption and water pressure. They are bound by the exact same brutal, metabolic arithmetic. As the evening slowly approaches and the angle of the sun lowers toward the horizon, the brilliant, luminous ceiling of the ocean begins to dim. The stark contrast softens. The seal's glowing silhouette slowly blurs and fades into the surrounding water. And in that moment, the evolutionary advantage shifts yet again. The twilight rapidly compresses the visibility for both the predator and the prey alike, heavily redistributing the balance of risk across the entire water column. What seemed like a state of certain, terrifying vulnerability at midday slowly dissolves into a mutual, dark ambiguity. The ocean does not belong permanently to the watcher, nor does it belong to the watched. It belongs exclusively to whoever understands its rapidly shifting optics at any given, fleeting moment. And so, the seal continues to swim near the surface, dipping its head into the water, not because it is careless, and not because it is foolish, but because biological life absolutely demands a constant, high-stakes negotiation with danger. Every single breath taken in the open water is an act of calculated, necessary exposure. Beneath the beautiful, mirrored skin of the sea, something massive may already be tracking the movement. It may already be measuring the distance. It may already be waiting for the perfect, fatal alignment. The calm above is never, ever a guarantee. It is merely the final, deceptive, glittering layer of a world where light itself can violently betray you. The circle closes so incredibly gently that nothing feels wrong at first. Hovering just a few inches above a scattered bed of coral rubble, a juvenile damselfish inspects a vibrant patch of green algae. It is an animal completely wired for survival, acutely aware of the shifting microcurrents and the exact positioning of its colorful neighbors. Its lateral line is primed, constantly reading the water for sudden, violent pressure waves that announce the arrival of a high-speed hunter. But right now, the water is utterly calm. There is no explosive surge from the deep. There is no sudden, terrifying shadow slicing rapidly through the sunlit water column. Instead, just a few feet away, a series of wildly elongated fins begins to slowly, silently unfurl. Thin, delicate rays spread outward in the water, opening like the delicate ribs of an ornate, deadly fan. The lionfish does not charge. It does not sprint. It expands. To watch a lionfish hunt is to watch a masterclass in architectural manipulation rather than physical speed. Their bodies are completely draped in a spectacular, almost theatrical array of venomous spines and trailing, feathery fin membranes. As the predator slowly moves forward, it extends these massive fins outward in wide, sweeping arcs, deliberately transforming what is actually a relatively compact fish into a massive, moving wall of striped, impenetrable geometry. These fins are not mere evolutionary decoration, and they are not simply a display of dominance. They are highly calculated behavioral tools. By slowly spreading them wide, the lionfish actively creates a massive visual barrier that artificially narrows the prey's perceived escape corridor. The damselfish continues to hover over the algae, its tiny eyes reacting to the subtle shifts in the dappled light and the gentle pull of the current, but the open water around it has already begun to shrink. Unlike the terrifying ambush predators that rely on blinding, straight-line acceleration, or the massive pelagic hunters that rely on grueling endurance, the lionfish entirely exploits the profound cognitive blind spots embedded deep within the brains of prey species. Reef fish have evolved over millions of years to be exquisitely attuned to high-velocity threats. Their highly sensitive lateral line systems are designed to instantly detect rapid, violent pressure changes in the water. Their visual cortex automatically prioritizes sudden, sharp movement against the complex, static background patterns of the reef. The lionfish bypasses this entire biological alarm system by moving at a meticulously deliberate, agonizingly slow pace. It approaches with the gentle drift of a piece of detached seaweed, absolutely minimizing any hydrodynamic turbulence and carefully avoiding any abrupt displacement of water. To the finely tuned sensory apparatus of the damselfish, absolutely nothing urgent registers. The predator is simply processed as another piece of the static reefscape. Its mesmerizing zebra-stripe pattern brilliantly breaks up its solid outline, allowing it to blend seamlessly with the dark shadows of the coral heads, the swaying branches of the sea fans, and the shifting shafts of sunlight. As the lionfish advances, inch by agonizing inch, it positions its body with cold, calculating orientation. It angles its massive, fanned-out profile to deliberately corral the tiny prey against a solid, structural boundary, a sheer rock face, a massive brain coral, or a dense thicket of staghorn branches. Every single, incremental fraction of a movement physically reduces the available space left in the water. The damselfish only begins to sense a confinement gradually. The illusion of the open ocean slowly fades. It nervously shifts left, looking for an exit, but the massive, striped fins of the predator instantly, smoothly adjust to block the path. The prey shifts right, and the opposing fins mirror the movement, maintaining a soft, yielding, but entirely persistent pressure. The escape routes are not being violently slammed shut. They are simply diminishing. The predator is dismantling the prey's freedom not through brute violence, but through the flawless application of applied geometry. Adding to this terrifyingly slow constriction is the lionfish's ultimate psychological weapon, the dozens of needle-sharp, venomous spines lining its dorsal, pelvic, and pectoral fins add a massive layer of deterrence to its physical encroachment. While the highly potent venom contained within these spines is biologically designed to be defensive rather than offensive, it is not used to subdue the prey. Its mere presence acts as a universal, visible warning system. It completely alters the rules of engagement on the reef. Massive predators that might otherwise disrupt the delicate hunt, a cruising reef shark or a large, territorial grouper, hesitate when they see the flared spines. They are acutely wary of the excruciating, paralyzing pain of envenomation delivered through a careless contact. Because of this, the lionfish moves within a virtually impenetrable, protective halo of toxicity. This invisible shield grants the predator an astonishing luxury in the wild, absolute, uninterrupted focus. It does not have to watch its own back. It can dedicate its entire cognitive capacity to the slow, methodical constriction of the prey's living space. Inside this relentlessly tightening perimeter, the prey's biology begins to turn against it. The damselfish's stress hormones rapidly spike. Cortisol floods its tiny bloodstream in direct response to prolonged, mounting perception threat, fundamentally altering its metabolic priorities. Its muscles twitch, fully primed for an explosive flight response. But flight requires a vector. It requires a clear direction. With every single subtle adjustment of the lionfish's massive fins, directional clarity completely erodes. The damselfish's nervous system frantically struggles to identify a viable path to safety, but everywhere it looks, it sees a wall of venomous spines and striped tissue. The predator has not even attempted to strike yet. It has not bared its teeth. It has simply, flawlessly shaped the battlefield until the prey has nowhere left to exist. And then, the lionfish employs a secondary, brilliantly devious tactic that further destabilizes the prey's completely overwhelmed cognition. As it closes the final few inches, the lionfish may actively blow gentle, highly directed jets of water directly toward the target. This behavior is not random, and it is not a byproduct of its breathing. It is an active manipulation of the fluid medium. The sudden, unexpected current physically hits the damselfish, violently disturbing its delicate buoyancy and forcing it to physically reposition itself to maintain balance. The terrified prey, frantically correcting its posture against these invisible currents, expends its vital energy while inadvertently pushing itself directly into positions that are far more advantageous for the predator's final capture. It is a cruel, invisible manipulation. The prey is literally steered by the water itself right into the kill zone. The final phase of the hunt unfolds with deceptive, devastating swiftness. Once the prey is completely confined within an impossibly narrow cone of space, its back against the coral, its sides blocked by the towering striped fins, the lionfish finally executes the strike. It is a remarkably short, rapid lunge. The massive jaws open, extending outward to create an instantaneous, powerful vacuum, engulfing completely trapped fish in a single, perfectly executed suction-driven motion. The violent strike is incredibly brief, taking only milliseconds, but absolutely succeeds because the prey's physical escape options were entirely dismantled minutes before the jaws ever moved. The profound fear generated by the lionfish is entirely cumulative. It is not the sudden, shocking jolt of a high-speed impact. It is the slow, dawning, horrifying realization that your fundamental freedom of movement has been quietly, systematically erased from the world. Ecologically, this astonishing hunting strategy reflects a deep, complex adaptation to the highly intricate environments of coral reefs. In a landscape defined by jagged limestone, sharp branches, and endless, twisting crevices, relying on blinding speed is incredibly dangerous. High-speed chases risk catastrophic collisions with a razor-sharp coral and waste a massive amount of metabolic energy in tight, unforgiving quarters. By opting to reduce the prey's mobility gradually, the lionfish effectively conserves its metabolic reserves while achieving a staggering rate of capture efficiency. Its entire hunting style is a masterpiece of energetic economy, relying entirely on spatial precision rather than athletic pursuit. Yet, the story of the lionfish deepens significantly, taking on a terrifying new dimension when viewed through the modern lens of ecological imbalance. In their native waters of the Indo-Pacific, lionfish exist within a highly complex, balanced web of evolutionary checks and balances. They have coexisted for millions of years with predators, parasites, and competitors that naturally modulate their population density. Large native groupers and specialized sharks occasionally prey upon the juveniles, and the established reef fish inherently recognize the slow, unfurling fins as a clear, present threat. The spatial trapping technique functions perfectly, but it functions within a balanced, sustainable web of life. However, in massively invaded ecosystems, most notably the Western Atlantic, the Caribbean, and the Gulf of Mexico, the biological narrative completely breaks down. Introduced by humans, the lionfish suddenly found themselves in an ocean where they have absolutely no natural predators. But far more devastating is the reaction of the native prey. The small fish of the Caribbean completely lack any evolutionary memory of the lionfish. They have never seen this creature before in the history of their genetic lineage. When a lionfish slowly approaches, unfurling its massive fins, the native damselfish, wrasses, and juvenile snappers do not recognize the slow encroachment as imminent danger. They completely fail to understand the geometry of the trap. This catastrophic mismatch between the predator's highly evolved behavior and the prey's entirely naive perception leads to staggering, apocalyptic predation rates. The lionfish act as an unchecked plague. They gorge themselves, drastically reducing the vital populations of herbivorous fish. the precise species that constantly graze on the reef, keeping the aggressive algae in check. As the lionfish consume the grazers, the algae is left to proliferate wildly, smothering the reef. Coral recruitment plummets. The physical structure of the reef begins to erode, and the entire ecosystem shifts toward collapse. The lionfish's slow, patient trap extends far beyond the individual, terrified fish. It reaches out to reshape and destroy entire, massive coastal communities. And yet, even amidst this terrifying dominance, the predator is not entirely absolute. The exact same biological traits that grant the lionfish its mastery over the reef also embed a profound, inescapable physical constraint. The massive, extravagant fins that perfectly create a cage for the prey also create a massive amount of hydrodynamic drag. The lionfish is a spectacularly terrible swimmer. If it is caught out in the open water, away from the protective structure of the reef, it is painfully sluggish and highly conspicuous. While its venomous spines deter many casual threats, they do not render the lionfish completely invulnerable. In recent years, massive Atlantic groupers and certain species of sharks have slowly begun to learn how to consume them, carefully circumventing the toxic spines through strategic, intelligent positioning and the application of immensely powerful jaws. The great narrative reversal emerges here in full force. The exact same anatomical fins that create an inescapable prison for the prey also relentlessly expose the lionfish to visual detection in the open ocean. Its ornate, beautiful silhouette, so brutally effective in the tight confinement of the coral labyrinth, becomes a massive, glowing liability in exposed, open environments. Without the complex physical structure of the reef to anchor its strategy, the lionfish's slow, geometrical advance loses all of its deadly potency. Still, within the dark coral labyrinths and the shadowed rubble fields, the technique remains an absolute nightmare. The damselfish's world slowly, inexorably narrows until every single option simply dissolves into striped fins. Movement becomes utterly futile, not because the predator is faster, but because the physical space required for movement no longer exists. The predator has successfully transformed the environment itself into a lethal instrument. The light filters softly across the flared, striped fins, casting shifting, hypnotic shadows that further confuse the prey's failing perception. The reef hums with a subtle, continuous movement of currents, completely unaware of the silent, horrific siege unfolding within its microscopic crevices. To a human diver observing from a distance, absolutely nothing dramatic appears to be occurring. It just looks like a beautiful, ornate fish hovering very closely to a smaller fish. Yet within that calm, completely silent facade, the lethal geometry is tightening its final knot. When the violent suction strike finally arrives, it feels incredibly abrupt to the observer, but to the predator, it is merely the calm, expected culmination of a mathematical process that was already completed minutes ago. The lionfish swallows, its throat expanding briefly, and then it simply resumes its incredibly slow, drifting patrol. Its massive fins fold back just slightly, the venomous spines remaining fully raised in a state of quiet, perpetual warning. Another small, unsuspecting fish drifts among the staghorn branches just a few yards away, entirely unaware that the physical boundaries of its freedom can be utterly erased without a high-speed chase, without a violent ripple in the water, and without a single, explosive motion. In this shadow theater of the reef, terror is a creature of infinite patience. It does not announce its arrival with blinding speed or crushing jaws. It arrives through incremental, invisible narrowing. It arrives through soft, yielding barriers that feel like mere coincidence until the exact moment they become absolute confinement. And by the time the realization of the trap finally dawns on the prey, the circle has already permanently closed. The pull is sudden, violently sideways and absolute. One moment, a vibrantly colored reef fish hovers just inches above a massive brain coral, its delicate fins flickering in effortless suspension, entirely attuned to the gentle, rhythmic swaying of the ocean current. It is a creature born to navigate the complex, three-dimensional openness of the water column. And in the very next instant, that vast world aggressively narrows into a jagged limestone crack no wider than its own body. Heavy jaws clamp down with bone-crushing force, not necessarily to sever and not to kill instantly, but to anchor. The Moray Eel does not chase its prey into the open water. It does not spiral in relentless, high-speed pursuit like a barracuda, and it does not coordinate in massive, terrifying packs like a pod of dolphins. It retreats, it pulls, and in that dark, violent retreat lies the true, unique terror of this encounter. The prey is not simply bitten. It is forcibly relocated. It is taken somewhere it was never meant to go. In the domain of the Moray Eel, the coral reef itself becomes a heavily weaponized instrument. Moray eels are the undisputed architects of confinement. Their incredibly elongated, heavily muscled bodies are designed not for the explosive sprinting of the pelagic hunters, but for the dark art of infiltration. They are perfectly evolved to slip seamlessly between the tightly packed, branching corals and slither deep beneath the heavy limestone overhangs with a bright, tropical daylight completely dissolves into permanent, suffocating shadow. To achieve this mastery of tight spaces, the physical anatomy of the moray is a marvel of evolutionary engineering. Its skull is remarkably narrow, yet heavily reinforced with dense bone, fully capable of withstanding the extreme lateral torsion generated as the eel violently twists and thrashes its massive body within the incredibly tight, unforgiving stone corridors. Lining its powerful jaws are rows of translucent, razor-sharp, backward-curving teeth. These teeth act as a biological ratchet system. They are designed to prevent the prey from ever sliding forward and breaking free once the initial, devastating seizure has occurred. Every struggle, every frantic attempt by the prey to pull away, only drives the curved teeth deeper into its own flesh. But the most remarkable, terrifying feature of the moray eel hides much deeper inside its throat. While the primary jaws are designed to grip and hold, the moray possesses a second, fully functional set of jaws known as the pharyngeal jaws. This is a mechanism straight out of a biological nightmare. Resting deep within the esophagus, these secondary jaws are equipped with their own set of sharp teeth and are attached to a highly specialized, elongated set of muscles. When the primary jaws lock onto a struggling fish, the moray does not simply swallow using the suction of water, like almost every other fish in the ocean. It cannot. Its head is too narrow, and the confined space of its burrow prevents the necessary displacement of water. Instead, the eel lunges its pharyngeal jaws forward, physically projecting them out of its throat and into the back of its own mouth. These secondary jaws violently clamp down on the prey, lock their grip, and then physically retract, violently dragging the struggling fish backward into dark, crushing confines of the eel's digestive tract. This unimaginable mechanism ensures that escape, even after the initial capture, becomes a literal, mechanical impossibility. The reef is not merely a beautiful backdrop for this violence. It is the essential infrastructure of the hunt. The massive coral formations create sprawling, three-dimensional labyrinths of winding channels, blind alleys, and deep overhangs. These are spaces that are fundamentally too confined for most fish to maneuver effectively once their forward momentum is violently disrupted. A standard reef fish, beautifully adapted for open water evasion, relies almost entirely on lateral bursts of speed, rapid, powerful tail beats that generate sudden acceleration across a physical distance. But inside a dark crevice, distance simply vanishes. The prey's body violently collides with unyielding stone. Its delicate fins scrape uselessly against the jagged rock. Its turning radius collapses to zero. The physical environment itself actively absorbs and neutralizes every desperate movement. Moray eels exploit this geometry with terrifying, calculated precision. They spend the vast majority of their lives waiting, perfectly still, with only their head protruding from a dark hole, the rest of their massive, muscular body tightly coiled within the hidden cavity. Their vision is notoriously poor. They do not scan the reef with the sharp, binocular focus of a shark or a tuna. Instead, they read the water chemically. Sensory pores lining their snout constantly sample the passing currents, highly attuned to the microscopic chemical traces of life. Olfaction entirely dominates their world. The eel can detect the faintest traces of amino acids dissolved in the seawater, reading the physical presence of prey through invisible scent gradients that are completely unreadable to sighted animals. To a moray eel, the ocean is a swirling, three-dimensional map of smell. When a fish inevitably ventures just a fraction too close to the hidden entrance of the burrow, the strike is incredibly short, violent, and explosive. The jaws snap shut with sudden, terrifying force. But instead of thrashing out into the open reef to secure the kill, the eel immediately shifts into reverse, pulling backward into the absolute darkness of the stone. The fear for the prey is not the initial, piercing pain in the teeth. It is the immediate, claustrophobic reality of spatial collapse. The bright, sunlit blue of the ocean fades instantly as the fish is dragged deeper and deeper into a jagged tunnel it cannot even see. The hard, limestone walls of the reef physically press inward, entirely removing any lateral escape paths. The flow of oxygenated water becomes severely restricted, utterly reducing the prey's ability to orient itself through the familiar cues of the ocean current. The eel's long, muscular body, securely anchored deep within its chosen cavity, uses the immense leverage provided by the surrounding rock surfaces to generate a pulling force that is far, far beyond what it could ever possibly produce out in the open water. Each backward, serpentine undulation of the eel's body wedges it more and more securely into the tight crevice, actively converting its stony surroundings into an unyielding fulcrum. Inside that crushing darkness, the pharyngeal jaws advance. They shoot forward, grip, and retract, mechanically ratcheting the terrified fish deeper into the throat. The reef's microenvironment heavily compounds the biological crisis for prey. The incredibly tight, enclosed spaces drastically reduce the circulation of oxygen, causing an immediate, massive increase in physiological stress on an animal that is already frantically struggling against total restraint. Elevated levels of carbon dioxide begin to pool rapidly in the confined water of the crevice, which aggressively disrupts the delicate acid-base balance in the prey's bloodstream, severely impairing its muscle function. As pure, blind panic exponentially accelerates the prey's respiration, the rapid depletion of oxygen dramatically hastens total muscular fatigue. The prey's own massive, desperate metabolic surge actively works against it, suffocating it in the dark. And yet, this terrifyingly effective, specialized strategy carries its own profound, evolutionary vulnerabilities. Moray eels, for all their fearsome, monstrous reputation, are absolutely not the dominant predators in the open water. Their elongated, serpentine bodies entirely lack the hydrodynamic efficiency of the sleek, pelagic hunters. If forced out of their holes, they cannot pursue fleeing prey across any real distance with sustained speed. Their absolute reliance on tight crevices reflects a massive evolutionary trade-off. They have traded open field agility for overwhelming power within extreme confinement. Out on the bright, exposed reef crests, morays are highly cautious, vulnerable creatures, frequently forced to retreat rapidly from larger, roaming predators such as massive groupers, reef sharks, and even triggerfish. This is the great narrative reversal of their existence. The deep, suffocating darkness that spells absolute doom for their prey is also the very source of the moray's total dependency. Remove the labyrinth of the coral, and the eel's terrifying advantage diminishes to nothing. In heavily degraded reef systems, where the complex coral cover rapidly declines due to mass bleaching events, warming oceans, or the destructive force of severe storms, the hiding spaces begin to shrink and disappear. The morays become physically exposed, their vital ambush sites reduced to rubble. Their hunting success plummets as the structural complexity of their world erodes. They are masters of a castle that is slowly crumbling around them. Within intact, healthy reefs, however, the eel's dark partnership with the environment extends far beyond merely using it as passive shelter. In one of the most fascinating, complex behavioral interactions in the entire marine world, some species of moray eels actively engage in cooperative hunting with the very groupers that might otherwise prey upon them in the open water. This astonishing phenomenon completely blurs the traditional, rigid lines of predator hierarchies. The massive grouper, incredibly powerful and fast in the open water but too bulky to enter the tight cracks of the reef, will actively approach a moray's burrow. It signals the eel with highly specific, rapid head shakes and complex body language, essentially recruiting the serpent to join a hunt. The moray, understanding the signal, emerges from its hole and slithers alongside the grouper. Together, they form an inescapable dual-threat network. The moray penetrates the incredibly tight, dark spaces that are entirely inaccessible to the bulky grouper, aggressively flushing the hidden, terrified fish out of their safe crevices. The fleeing prey is driven out of the dark and straight into bright, open water, where the massive jaws of the waiting grouper instantly strike. Conversely, If the prey attempts to flee the grouper by diving deep into the safety of the rock, it swims directly into the jaws of the waiting moray. Here, the darkness and light function as perfectly synchronized, alternating traps. The prey is ruthlessly shuttled between two entirely different realms of physical disadvantage. The Moray Eel, historically perceived by science as a strictly solitary, confined monster, reveals itself to be a highly intelligent node in a dynamic, cooperative hunting network. Yet, even in its solitary hunts, the eel's entire existence depends on the grand architecture of the environment. Coral reefs are massive, three-dimensional living mosaics, intricately shaped by thousands of centuries of slow calcification and gradual erosion. Every single cavity, every crack, and every overhang offers vital microhabitats that naturally concentrate the smaller prey species desperately seeking shelter from the open water hunters. By strategically positioning itself directly within these high-traffic intersections, the moray effortlessly leverages the grand ecological patterns to its absolute advantage. It does not need to roam the ocean. It merely occupies a central node in the massive network of life and movement. The prey's perspective is entirely shaped by that exact same architecture. Small reef fish rely heavily on intimate, memorized familiarity with the local terrain to successfully evade predators, instinctively darting into the specific holes they have memorized since they were juveniles. But that familiarity is a double-edged sword that can violently betray them. The very same limestone crevice that generously offered absolute safety yesterday may house a waiting, coiled eel today. Behavioral ecology teaches us that shelter selection for small fish involves a constant, highly stressful risk assessment. They must endlessly balance the absolute need for physical protection from the fast, open water hunters against the terrifying exposure to the hidden ambush predators waiting within the refuge itself. The reef offers safety, but never, ever universally. As the eel finally tightens its crushing hold deep inside the crevice, the mechanical, biological act of consumption unfolds with clinical, terrifying efficiency. The primary teeth completely prevent any backward motion. The inner, pharyngeal jaws continuously advance and retract in a rhythmic, inescapable cycle. The eel's massive, muscular body undulates violently against the unyielding rock, perfectly using the friction of the stone to anchor itself while generating a massive, pulling force. The prey's frantic struggles finally begin to weaken as the massive oxygen debt accumulates in total, irreversible muscular exhaustion sets in. The darkness becomes absolute and complete. Yet, the story of the reef does not end with this inevitability. Certain prey species have evolved their own brilliant strategies to counter this specific, terrifying form of crevice predation. Tiny cleaner wrasses and specialized shrimp, for example, often operate in highly complex mutualistic relationships with the moray eels. They brazenly swim directly into the open, venomous jaws of the eel to diligently pick away dead skin and irritating parasites. They drastically reduce their likelihood of being eaten by establishing these highly recognized behavioral contracts. Other species of reef fish actively secrete thick, highly viscous mucus layers across their scales that drastically reduce the physical grip efficiency of the eel's teeth, allowing them to slip free in the crucial milliseconds of the first strike. Others adopt body shapes that are simply too broad and tall to be easily dragged into the narrow, restrictive cavities, actively limiting their physical vulnerability to being pulled inward. Even the simple timing of their daily foraging, choosing to remain in the riskier open water specifically during the peak twilight hours of moray activity, reflects a deeply ingrained, adaptive response to this highly specialized, terrifying predator. The moray eels themselves must endlessly navigate the severe physical constraints of their chosen, dark environment. Once inside those incredibly tight crevices, their own mobility is heavily restricted. If a much larger predator, such as an aggressive reef shark, manages to locate them and attempts to violently extract them from the hole, the eel's retreat options are severely limited. Their absolute reliance on the darkness is deeply double-edged. The exact same limestone tunnels that amplify their terrifying pulling power can instantly become inescapable stone tombs if the reef structure violently shifts, breaks, or collapses. The coral reef remains a silent, overarching protagonist in this ancient, violent encounter. Its sprawling, branching corals, its heavy overhangs, and its scattered rubble fields absolutely dictate who controls the movement and who controls the visibility. Out in the vast, open sand flats located just adjacent to the reefs, morays are almost rarely encountered actively hunting. They are incredibly vulnerable there. They always return to the dark labyrinth. They return to the specific architecture that magically transforms them from slow, elongated fish into the undisputed, terrifying masters of confinement. For the terrified prey caught in the jaws, the true horror lies not in the razor sharpness of the teeth and not in the venom, but in the overwhelming, suffocating sensation of being forcibly relocated far beyond the reach of light and leverage. Movement entirely ceases to function as a mechanism for escape. Visibility violently narrows to absolute nothingness. The beautiful, vibrant reef that once promised protection and life instantly becomes a dark, jagged corridor leading only inward, deeper and darker. And yet, across the sprawling expanse of the reefscape, the grand biological balance persists. Moray eels actively regulate the explosive populations of the smaller fish, actively preventing the catastrophic overgrazing of the delicate coral polyps and maintaining the long-term stability of the entire ecosystem. Their dark, violent predation directly contributes to the trophic equilibrium, actively shaping the species composition of the reef over centuries. The terrifying, unseen act of dragging a single fish deep into the darkness reverberates outward, heavily sustaining the overall health and massive biodiversity of the entire ocean. As the heavy ocean currents subtly shift, and the angles of the penetrating light slowly change to the sinking, late-afternoon sun, the moray's sleek, menacing head once again slowly protrudes from its chosen, darkened cavity. Its massive jaws open and close in a slow, rhythmic, hypnotic breathing cycle to ventilate its gills. To the untrained eye, it appears almost completely passive, a benign, unmoving presence seamlessly integrated into the rock. But deeply hidden beneath that perfect, deceptive stillness lies a terrifying, absolute strategy refined by millions of years of ruthless evolution. It is a strategy of pure, dark patience. Do not chase the world. Let the world come close. And then, violently, inescapably, remove it from the light. The sprawling reef slowly returns to its quiet, beautiful choreography of grazing and gliding. Schools of vibrant fish weave effortlessly through the branching coral, supremely confident in their familiar, sunlit terrain. Yet somewhere deep within that complex, three-dimensional maze, the darkness waits. It does not wait as a mere absence of light, but as a heavily controlled, weaponized space. And entirely within that suffocating space, the moray reigns supreme, not by dominating the vast, open water, but by achieving absolute, terrifying mastery over the hidden places where escape becomes a physical impossibility. The line breaks. A young seal surges through the freezing, heavily oxygenated water alongside its massive colony. Hundreds, sometimes thousands, of sleek bodies are packed tightly together, moving as a single, fluid entity against the jagged edge of the drifting ice shelf. They are engaged in the ancient, unwritten mathematics of the wild. Each individual animal is subconsciously relying on the sheer geometry of numbers for its absolute protection. In a massive crowd, the statistical probability of being the one chosen to die drops to a fraction of a percent. The vigilance is shared. Thousands of eyes scan the deep blue. Thousands of sensitive whiskers read the subtle currents. It is a collective, shared armor forged from proximity and confusion. Then, the surface of the ocean physically detonates beneath them. Massive, contrasting forms of absolute black and blinding white rise from the crushing depths in perfectly coordinated, terrifying arcs. They slice directly through the center of the dense formation, but they do not strike blindly. They do not snap their massive jaws indiscriminately into the crowd of fleeing bodies in a chaotic frenzy of hunger. They move with cold, surgical precision to achieve one singular goal: fracture. The young seal feels a sudden, violent shift in the current. The comforting, buffering bodies of its kin peel frantically away from its flanks, scattering in a blinding cloud of bubbles and panic. And in that single, catastrophic disruption, the protective arithmetic of safety completely collapses. The seal is no longer an anonymous fraction hidden within a massive whole. It is suddenly, terrifyingly one. Orcas do not begin their hunts with the kill. The kill is merely the final, inevitable punctuation at the end of a long, highly complex sentence. They begin entirely with the concept of separation. Deep beneath the waves, an intricate, invisible web of communication is pulsing to the water in layered, high-frequency clicks, squeals, and haunting whistles. Each specific call is densely encoded with vital tactical information about position, speed, intention, and perfect timing. The brains of these apex predators are among the most complex, highly folded, and neurologically advanced structures in the entire biological world. Their paralimbic clefts, the area of the brain associated with spatial reasoning, emotional intelligence, and complex social processing, are incredibly enlarged, rivaling and in some aspects exceeding those of humans. This staggering neurological architecture supports not only brilliant individual cognition, but terrifyingly advanced level of cooperative, social strategy. When hunting highly aware, agile prey like seals clustered around shifting ice flows or massive, defensive schools of fish, orcas deploy military-grade tactics that aim not at immediate physical capture, but at total structural disassembly. The group must be broken before the individual can fall. The young seal, realizing its sudden isolation, frantically accelerates toward the perceived safety of thicker ice. But an enormous, black dorsal fin surfaces directly ahead of it, cleanly blocking the most efficient escape vector. As the seal pivots in panic, another massive body sweeps in from the darkness below, deliberately releasing a thick, confusing stream of bubbles that actively obscures the seal's depth perception and masks the acoustic signatures of the hunters. The seal twists again, but every single frantic turn only exposes a new, vulnerable flank. The orcas are actively exploiting the hydrodynamic pressure of their own massive bodies to meticulously herd the prey out into the open water, pushing it further and further away from the physical, rigid shelter of the ice. If the seal manages to haul itself out of the water and onto a floating sheet of ice, the hunt does not end. It merely shifts into a new, even more terrifying phase of physical engineering. In the freezing waters of the Antarctic, highly specialized pods of orcas have developed a technique that borders on the unbelievable. When a seal is resting safely on an ice floe out of reach of their jaws, the orcas do not simply wait for it to make a mistake. They manufacture the mistake. The massive animals swim backward, moving far away from the ice, aligning themselves shoulder to shoulder in perfect, synchronized ranks. Then, on an invisible, acoustic command from the pod's matriarch, they charge the ice at high speed. Just before impact, they dive synchronously, their massive, combined bulk displacing a localized mountain of water. This synchronized dive generates a powerful artificial wave. The wave surges forward, crests over the top of the ice platform, and physically washes the terrified seal right off its temporary fortress and back into the waiting, lethal jaws of the pod below. This is not instinct. This is applied physics. This is calculated, cultural engineering passed down through generations. But even out in the open, pelagic pursuit, the primary objective of the pod is never brute, immediate force. It is the absolute maintenance of isolation. Within a colony, the heavy cognitive burden of vigilance is distributed. Eyes scan in multiple, overlapping directions, and the subtle behavioral alarm cues ripple instantaneously across the collective. But the exact moment separation occurs, that shared vigilance violently collapses inward. The isolated seal must now frantically monitor every single direction, every shifting shadow, every pressure change in the water, entirely alone. Its cognitive load spikes massively. Stress hormones, adrenaline and cortisol, surge through its bloodstream in toxic, overwhelming amounts. This biochemical flood drastically alters the seal's heart rate, narrows its visual perception to a state of tunnel vision, and heavily impairs its long-term decision-making. The seal's movements, once fluid, beautifully adapted arcs of underwater grace, rapidly degrade into erratic, frantic, desperate bursts. Its internal anaerobic reserves begin burning in unsustainable, explosive rate under the crushing weight of pure panic. The orcas, by terrifying contrast, maintain absolute, terrifying composure. Their unique physiology perfectly supports both overwhelming physical power and seemingly infinite endurance. Their massive bodies, heavily insulated by incredibly thick layers of blubber, easily sustain their core energy in the freezing water, while their enormous, heavily muscled tail flukes deliver a smooth, continuously controlled acceleration. Unlike the great white sharks or the barracudas that rely on the immediate, explosive element as a prize to capture their prey, orcas are fully prepared to modulate their speed to perfectly match the degrading fatigue curves of their targets. They understand, through a combination of deep, predatory instinct and highly refined cultural learning taught by the matriarchs, that pure panic rapidly accelerates total physical exhaustion. The exact moment of being singled out from the crowd is not only a terrifying spatial reality, it is a deadly metabolic trap. Within the pursuing pod-specific, defined roles emerge with absolute fluidity. One massive individual may aggressively drive the prey from behind, constantly snapping its jaws just inches from the seal's rear flippers to force it to swim faster and burn more oxygen. Another orca will flank wide to the left, preventing any lateral turns towards safety, while a third effortlessly cruises far ahead, casually waiting to intercept the prey when it inevitably attempts to double back. This breathtaking, terrifying choreography reflects nothing of random, chaotic convergence. It is the pure manifestation of cooperative hyperintelligence. These specific lethal hunting techniques are actively transmitted across generations, forming deep, localized cultural traditions that are completely unique to specific family pods. In some regions of the world, resident orcas specialize entirely in hunting massive schools of salmon, utilizing different acoustic patterns and herding techniques. In others, transient pods specialize exclusively in hunting marine mammals, dolphins, porpoises, and even the massive calves of gray whales. The strategy of absolute separation seamlessly adapts to the specific target species, but the core philosophy remains identical: divide and conquer. The terrified seal desperately attempts to adjust its course, hoping to miraculously rejoin its distant, scattered colony. But the gap of dark water has widened significantly. The orcas effortlessly reposition their massive bodies to completely prevent reintegration, physically using their bulk as moving, impenetrable walls of flesh and blubber. This is the ultimate psychological turning point within the hunt. Just minutes ago, the seal was heavily buffered by the confusion of the crowd and the shared defense of the colony. Now completely alone, it has become a singular, high contrast, desperately beating hard against a vast, empty canvas of the open ocean. The true fear experience in this moment is not just the imminent threat of death. It is a sudden, violent stripping away of communal armor. It is the realization that the world has narrowed down to just you and the highly intelligent monsters that are slowly running you to death. Ecologically, this specific, terrifying tactic of isolation exerts a profound, far-reaching pressure on the behavior of prey species across the globe. Seal and sea lion colonies deliberately choose their haul-out sites with an obsessive focus on immediate proximity to shallow reefs, thick kelp forests, or shoreline refuges, constantly, nervously balancing their need for rich feeding grounds against their terrifying exposure to the black and white hunters. Massive schools of fish actively alter their ancient, generational migration routes to widely bypass known orca territories. The mere psychological threat of separation actively shapes habitat selection, reproductive timing, and the physical density of group cohesion across entire, massive ecosystems. The ocean is molded by the fear of the pod. Yet, the narrative of the apex predator absolutely does not end in a state of unilateral, invincible dominance. Orcas, despite their unrivaled intelligence and their absolute position at the very top of the marine food web, are not immune to profound ecological constraints. Their highly complex cooperative hunts require incredibly stable social structures and a massive, reliable density of available prey. Severe declines in global fish stocks, or the collapse of local marine mammal populations due to shifting climates, can violently fracture these tight-knit pods, leading to severe nutritional stress and the breakdown of their generational hunting cultures. Furthermore, because they sit at the absolute apex of the trophic pyramid, they are terrifyingly vulnerable to the bioaccumulation of human pollutants. Heavy metals, PCBs, and industrial toxins wash into the sea and are absorbed by the plankton, eaten by the fish, consumed by the seals, and finally, heavily concentrated directly within the thick blubber of the orcas. These invisible, synthetic poisons actively compromise their immune systems, disrupt their hormonal balances, and severely crash their reproductive success rates. The ultimate predator, the master of isolating others, is itself incredibly vulnerable to the slow, invisible fragmentation of its own environment. There is also a massive, hidden risk embedded directly within their own brilliance and specialization. Pods that culturally focus exclusively on one particular prey type, such as resident pods that only eat specific species of salmon, often stubbornly struggle to adapt when those specific prey populations suddenly decline. Their deep cultural knowledge, which was once their greatest evolutionary advantage, can suddenly become a rigid, fatal limitation if their behavioral flexibility is reduced. Separation as a hunting tactic also depends heavily on predictable, understood group behavior from the prey. When the prey dynamically adapts, actively altering their movement patterns or discovering new, inaccessible refuges deep within the coastal geography, the orca strategy must rapidly evolve or the pod will starve. Returning to the immediate violent theater of the open water, the seal's frantic movements finally begin to slow. The inevitable is taking hold. Its precious oxygen stores are rapidly diminishing as the repeated, desperate, high-speed dives completely deplete its muscular reserves. The orcas, by terrifying contrast, are hardly breathing hard. They casually surface to breathe in perfectly coordinated, relaxed intervals, effortlessly conserving their massive energy. They are air-breathing mammals, exactly like the prey they are hunting, but their vastly larger lung capacity, combined the incredibly efficient storage of oxygen directly in their dense muscle tissue, allows them to endure far longer dives and maintain relentless, sustained pressure. They brutally exploit this massive physiological advantage, deliberately driving the exhausted seal into agonizing, endless cycles of forced submergence. Every time the seal desperately breaks the surface for a gasping breath, a massive black shape surges over it, forcing it back down into the crushing dark before its lungs can fully inflate. Eventually, the inevitable math closes a final distance. The orcas close the circle. The final strike is rarely a chaotic frenzy. It may involve a calculated, high-speed ramming with a reinforced snout to shatter ribs and cause internal bleeding. It may involve a devastating, perfectly timed tail slap designed to instantly stun the prey and break its spine. Or it may involve a synchronized, cooperative bite from multiple angles. The kill itself is swift, violent, and entirely decisive. But it is the long, agonizing, psychological isolation that preceded the physical violence that truly ensured its inevitability. Without that highly calculated separation, the young seal might have easily remained just one indistinguishable, anonymous body hidden safely within the chaotic, swirling crowd of the colony. Alone, it simply became a mathematical target that could not miss. As the feeding concludes, the ocean slowly regains its deceptive, freezing calm. Miles away on the jagged ice, the remaining seals cluster even tighter together, nervously adjusting their dense formation. Their collective behavior has been permanently, subtly altered by the loss. They will haul themselves out of the water, slightly differently tomorrow. They will perhaps choose thicker ice, or shift the physical position of the colony closer to the shallows. The orcas, too, silently adjust their massive patrol routes based on the success, the required energy expenditure, and the resistance encountered during the hunt. Predator and prey remain permanently locked in a brutal, highly adaptive dialogue of survival and death. But the deeper, most terrifying reversal of this entire narrative lies in the sudden realization that the overwhelming power of the orca does not stem solely from its massive physical strength, its crushing bite, or its sheer, terrifying speed. It stems entirely from its social cohesion. A solitary orca, separated from its family, would struggle immensely to dislodge a healthy seal from a complex ice flow or to meticulously dismantle a massive, defensive school of fish. It is the neural network of the family that creates the dominance. The apex predator that perfectly singles out an individual relies entirely on the absolute, unshakable collective unity within its own kind. Separation only works as a weapon because flawless, telepathic cooperation precedes it. And in a broader, far more tragic sense, the orcas themselves are currently being violently isolated by forces they cannot fight. Massive noise pollution from global industrial shipping lanes severely interferes with their delicate echolocation and their complex vocal communication. The deafening mechanical roar of boat engines physically fragments the pods acoustically, completely drowning out the subtle whistles and clicks that coordinate their movements. When their ancient calls are masked by this endless, anthropogenic sound, their flawless coordination falters. The brilliant hunter that depends entirely on synchronized movement becomes tragically disoriented, isolated, and lost in a sea suddenly filled with an impenetrable, blinding wall of mechanical noise. Still, out within the freezing, pristine polar waters where the ice still drifts in massive, silent cathedrals and true silence occasionally reigns, the ancient drama continues to endlessly repeat. A colony gathers. A pod approaches. The very first disruption is incredibly subtle, just a shifting shadow in the deep blue, and then it is immediately catastrophic. The protective arithmetic of safety violently fractures. One single individual drifts just slightly beyond protective, chaotic edge of the mass. In that exact, fatal instant, everything changes. The seal is no longer part of the crowd. It is no longer buffered by the math of the colony. It is a single, isolated, terrified heartbeat suspended alone in the massive, crushing open water. The Orcas smoothly adjust their formation, silently narrowing the dark corridor of escape. They are patient, they are precise, and they are incredibly intelligent. The ocean, vast, freezing, and utterly indifferent, offers absolutely no shelter. When the geometry of numbers finally dissolves, and as the massive black and white forms rise once more from the deep, carving perfect, lethal arcs against the gray, turbulent surface, the ultimate lesson reverberates through the entire ecosystem. Protection is collective, and the exact moment it breaks, survival becomes entirely, hopelessly solitary. The expansion begins as a deep, autonomic reflex older than memory itself. Down in a vibrant, chaotic sprawl of the coral reef, a small, unassuming fish is quietly going about its life. It moves with a slow, almost comical hovering motion, its compact body propelled by the rapid, fluttering synchronization of its pectoral and dorsal fins. It is a mid-level consumer, meticulously scanning the limestone for hard-shelled invertebrates, fully engaged in the mundane mathematics of foraging. The surrounding water is clear, bathed in the brilliant, fractured light of the tropical sun. There is no immediate tension, but in the ocean, tranquility is only ever a temporary state of grace. A shadow rushes forward from the periphery of the reef. It is a massive, predatory grouper, its eyes locked on a small, slow-moving target. The predator does not rely on complex stealth or protracted pursuit. It relies on the sudden, overwhelming application of size and suction. But as the shadow closes in, the prey does not dart away in a frantic, desperate sprint. It does not attempt to outrun the massive jaws, because evolution has already mathematically proven that it cannot. Instead, the pufferfish commits to a profound, instantaneous physical transformation. Its jaws open wide, and it inhales the surrounding ocean with a sudden, violent urgency. What happens next is a masterpiece of radical biological engineering. The stomach walls of the pufferfish, normally folded tightly in upon themselves like an intricate origami puzzle, begin to unfold in a fraction of a second. These highly specialized tissues are embedded with incredibly elastic connective fibers, perfectly designed to allow for rapid, massive distension without tearing or rupturing. The fish operates as a living, frantic pump. Water violently floods inward through its mouth and gill openings, bypassing the digestive tract and filling this highly specialized expansion chamber. Within mere seconds, the physical reality of the fish completely changes. Its overall volume wildly multiplies, expanding to 3 or 4 times its original size. It physically transforms from a streamlined, hovering swimmer into a massive, taut, spiked sphere. The muscles of its abdomen stretch to absolute limits rarely reached in calm conditions. As the skin tightly stretches over this rapidly swelling mass of water, hundreds of highly modified scales, which are in biological reality razor-sharp dermal spines, are violently erected. They stand straight outward, completely converting the fish's smooth, unassuming exterior into a terrifying field of rigid, piercing projections. The illusion of absolute invulnerability inflates right along with the body. The pufferfish does not flee. It commits entirely to defense, trusting its life to the pure geometry of intimidation. For the approaching grouper, the physical parameters of the hunt have instantaneously, disastrously shifted. Reef hunters like groupers and massive snappers are what marine biologists classify as gape-limited predators. They do not possess the slicing teeth of a shark or the biting mechanics of a mammal. They rely almost exclusively on the physics of suction feeding. They rapidly expand their massive buccal cavities, their mouths and throats, to create a sudden, violent vacuum, drawing the prey inward through negative pressure and swallowing it completely whole. But a fully inflated, spherical pufferfish fundamentally disrupts that exact physical mechanism. Its violently increased diameter suddenly vastly exceeds the maximum physical limits of the predator's open jaws. It literally cannot fit. And even if a massive predator attempts to force the issue, the rigid, protruding spines immediately lodge painfully into the incredibly soft, highly sensitive tissues of the predator's lips and the lining of its mouth. The predator's jaws meet unyielding resistance and excruciating pain, not yielding flesh. The math of the suction strike is instantly broken. Faced with this sudden, painful impossibility, the predator will very often simply release a sphere, thoroughly deterred by the physical discomfort and the absolute mechanical inefficiency of the attack. For countless, untold generations across millions of years, this spectacular defense mechanism has worked often enough and successfully enough to fully justify its staggering evolutionary cost. But here is where the narrative takes a dark, terrifying reversal, because inflation is not actually armor. It is merely posture. It is a grand, physical bluff. If the predator does not immediately retreat, if the initial shock of the spines is not enough to break the hunter's resolve, the pufferfish's grand assumptions of safety begin to rapidly, violently fail. Not all hunters in the ocean are forced to swallow their prey whole. Some predators bite. If the shadow approaching the reef is not a suction-feeding grouper, but a roaming reef shark, the entire dynamic of the encounter changes. Sharks possess rows of highly serrated, razor-sharp teeth that are perfectly designed for violently slicing and tearing through flesh, rather than relying on the physics of the vacuum. To a shark, the sudden increase in the physical size of the prey is less a mechanical deterrent and more of a suddenly enlarged target. A determined, hungry predator may simply grip the inflated sphere in its massive jaws and violently shake its head from side to side, actively tearing at the tightly inflated tissue, despite the piercing of the spines. And in this horrifying scenario, the pufferfish's ultimate defense immediately becomes its most fatal vulnerability. Its body, stretched paper-thin and extended far beyond its normal, relaxed contour, becomes incredibly taut and desperately vulnerable to a single, deep puncture. The very rapid, massive expansion that served as a visual warning and a physical barrier now tragically exposes a vastly larger surface area to a lethal, slicing attack. But the terror of this encounter is not merely external. Inside the heavily inflated, pressurized sphere, a massive, unseen physiological crisis is rapidly escalating. Inflation is not a casual, effortless trick. It is a massive, life-threatening metabolic gamble. To maintain this rigid, expanded shape, the dense muscle fibers lining the pufferfish's abdomen must remain violently, continuously contracted. This sustained muscular strain burns through the fish's cellular energy at a catastrophic rate, consuming its precious internal oxygen reserves in mere seconds. Furthermore, the sheer, crushing physical volume of the massive water balloon expanding inside its own body cavity aggressively compresses the fish's internal organs. Most critically, its gills, the delicate, feathery structures required to extract oxygen from the water, are heavily restricted by this massive internal distension. They are forced to operate under severely suboptimal, restricted flow conditions right at the exact moment the fish's body is demanding maximum oxygen output. Blood circulation violently shifts to accommodate these massive, unnatural internal pressure changes. Because of this brutal physiological reality, inflation cannot be sustained indefinitely. It is strictly designed by evolution as a brief, shocking deterrent, absolutely not as a prolonged, enduring siege. The true, paralyzing horror of the situation, the moment of terrible realization, if one can speak of biological realization in simple neural terms, occurs when the sheer resistance of sphere does not immediately produce a retreat from a predator. When the predator's grip tightens instead of loosening, the pufferfish is doomed by its own design. Fully inflated, it is incredibly buoyant and entirely, hopelessly clumsy. It completely loses the ability to maneuver effectively, entirely losing the ability to direct any kind of rapid escape. Its delicate fins, now splayed awkwardly and uselessly outward against the massive curves of its swollen body, simply cannot generate any efficient, forward propulsion. what was meticulously evolved to completely immobilize a predator has, tragically and fatally, completely immobilize a prey itself. It becomes a helpless, floating balloon, drifting utterly exposed in a hostile, unforgiving space. And yet, in the complex, layered warfare of the coral reef, the defense was never singular. It was never just about water and spines. Deeply embedded within the liver, the ovaries, and the very skin tissues of the pufferfish lies tetrodotoxin, widely known as TTX. It is one of the most potent lethal neurotoxins discovered in the natural world. But the fascinating, bizarre truth of this chemical weapon is that it is not actually synthesized by the fish itself. It is actively produced by highly specialized, symbiotic bacteria that permanently reside within the fish's organs, engaging in a mutually beneficial relationship that turns a host into a swimming bioweapon. This terrifying compound operates with ruthless biochemical efficiency. It actively targets and aggressively blocks the fast sodium channels located in the membranes of nerve cells. By physically plugging these microscopic cellular pores, the toxin completely prevents the firing of electrical action potentials. It instantly severs the communication between the brain and the body, inducing a rapid, total, and ultimately fatal muscular paralysis in any predator foolish enough to ingest a sufficient quantity. The diaphragm fails. The heart stops. The predator suffocates. But here lies the grim, evolutionary paradox of the pufferfish's ultimate weapon. The toxin does not act instantly through mere physical contact. It requires deep ingestion to take lethal effect. The pufferfish must literally be bitten, crushed, or fully consumed for its ultimate defense to exact its terrible revenge. The neurotoxin cannot save the life of the individual fish currently being eaten. It can only guarantee the death of the predator that eats it. Therefore, the entire act of inflation serves partly as a massive, unmistakable billboard of advertisement. It is a highly visible, physical warning permanently paired with invisible chemical deterrents. In complex reef ecosystems where highly intelligent predators actively learn through painful, traumatic experience, the bizarre shapes and the brightly colored, high-contrast patterns of the pufferfish visibly signal its extreme toxicity. A single, agonizingly failed attempt by a juvenile shark or a massive reef fish to sample a pufferfish can permanently, neurologically imprint an absolute avoidance behavior deep into its brain. This is known in biology as aposematism. The illusion of safety for the entire species is heavily reinforced by the inherited and learned memory of the predators. But predators are not uniform in their cognition, their desperation, or their biological tolerance. In times of severe ecological stress or starvation, some desperate species may attempt to sample the pufferfish cautiously, biting and quickly releasing the tissue, without actually ingesting a fully lethal dose. Other, highly specialized predators, such as certain species of sea snakes or massive tiger sharks, may slowly evolve a partial, genetic resistance to the neurotoxins through millions of years of intense selective pressure. The puffer's ultimate chemical defense, incredibly powerful and lethal though it undeniably is, can absolutely never guarantee total, universal immunity from predation. Moreover, the sheer ecological balance of the reef deeply complicates the narrative of this bizarre creature. Pufferfish are absolutely not apex predators themselves. They are highly active, mid-level consumers. They spend their days meticulously feeding on hard-shelled invertebrates, grazing on algae, and slowly picking to the limestone. Their specialized, heavy, beak-like teeth are perfectly evolved to crush the thickest, hardest shells of the reef, actively regulating the explosive populations of crabs, sea urchins, and benthic mollusks. Their continued, daily survival heavily influences the physical composition of the entire reef indirectly by constantly shaping the prey communities below them. If the grand bluff of inflation repeatedly fails, and massive pufferfish populations begin to rapidly decline due to overpredation or human interference, massive, unseen trophic cascades immediately ripple outward. The urchins and crabs overpopulate, violently altering competitive dynamics and the physical structure of the coral itself. The life and death of the spiked sphere are deeply, inextricably woven into the health of the entire ocean. The terrifying inflation response itself also carries severe, life-threatening risks completely independent of the predators. If the deeply ingrained reflex is triggered excessively, or if it occurs under highly stressful, artificial conditions near the surface, The panicked pufferfish may inadvertently swallow massive gulps of atmospheric air instead of seawater. This is a biological catastrophe. Air permanently trapped inside the massive, distended expansion chamber can permanently impair the fish's delicate buoyancy control. It acts exactly like an internal life jacket that cannot be removed. The helpless fish is violently dragged upward, left floating upside down, permanently stranded right at the surface of the water, hopelessly exposed to the tearing beaks of predatory seabirds and the crushing jaws of surface-feeding sharks. It cannot swim down. It cannot right itself. To successfully deflate, the fish absolutely requires both time and a state of complete physical safety. Without both of those rare commodities, the fish simply becomes a tragic, awkward, dying balloon drifting endlessly in a hostile, sunlit void. Yet, as with every single interaction in the ocean, there is always a counter-tactic. There is always an evolutionary reversal hidden within the vulnerability. The apparent tragic failure of the inflation defense reveals a deeper truth. It was never designed by evolution as a solitary, foolproof salvation. It is merely one vital part of a highly complex, deeply layered strategy seamlessly combining morphology, biochemistry, and advanced behavior. Pufferfish are not merely slow, inflatable spheres waiting to be attacked. They are highly cryptic, intelligent feeders, fully capable of seamlessly blending into the rough, broken textures of the reef when they're calm. The complex, highly evolved pigment patterns on their skin actively disrupt their physical outlines, drastically reducing their probability of detection long before a physical conflict ever arises. Inflation is strictly the absolute last resort, never the first line of defense. When a determined predator aggressively persists despite the massive inflation, actively circling the spike sphere and looking for an angle, some highly experienced pufferfish actively exploit the element of absolute surprise hidden deeply within their own extreme vulnerability. In a fraction of a second, the fish can execute a sudden, violently controlled deflation. It rapidly expels a massive volume of trapped water, using the forceful contraction of its stretched abdominal muscles to convert all that stored, elastic tension into a sudden, explosive burst of backward movement. The massive predator, whose brain was fully anticipating continued, awkward immobility from the spherical target, may hesitate in sheer confusion for just a fraction of a second. And in that single, tiny window of cognitive delay, the suddenly streamlined, deflated fish violently slips away, darting deep into the safety of the dark coral. This desperate tactic demands absolute, flawless timing and heavily relies on whatever tiny energy reserves the fish has left, and absolutely cannot be deployed repeatedly. But in rare, incredible moments of survival, the sudden surrender of the defensive posture violently transforms into the ultimate opportunity for escape. The sprawling, jagged architecture of the reef itself also heavily participates in this life-or-death drama. A fully inflated pufferfish, violently wedged deep among the tight, branching arms of the staghorn corals or shoved into a narrow limestone crevice, instantly creates a massive, insurmountable spatial complication for any large predator attempting to maneuver its jaws into position. The rigid, erected spines aggressively catch and lock against the unyielding coral limbs, acting exactly like grappling hooks, making physical extraction incredibly difficult, if not utterly impossible. In such highly confined environments, the inflation defense instantly regains its absolute efficacy, not merely through visual intimidation or chemical threat, but through pure physical entanglement. The habitat actively amplifies the defense. Physiologically, the pufferfish's sheer biological tolerance to this immense internal water pressure is nothing short of a miracle. Deeply woven connective tissues and heavy, reinforced collagen fibers actively support the stomach walls, mechanically preventing a fatal, catastrophic rupture during the incredibly rapid, violent expansion. Complex, highly evolved enzymatic pathways frantically work overtime to regulate the fish's internal electrolyte balance as the massive flood of raw seawater rushes inward. These invisible, cellular mechanisms underscore the incredible truth that inflation is absolutely not a random, chaotic swelling. It is a highly coordinated, flawlessly orchestrated symphony of muscle, membrane, and advanced fluid dynamics. Still, despite all the miracles of its anatomy, the grand illusion of absolute invulnerability remains terrifyingly fragile. When a massive, hungry predator simply refuses to be deterred by the shape, the spines, or the thread of the toxin, the pufferfish violently confronts the absolute, terrifying limits of its own evolutionary design. Its grand defense instantly transforms into its greatest liability as its vital mobility completely vanishes and its metabolic demands skyrocket beyond sustainable limits. The beautiful, spiked illusion violently collapses under sustained physical pressure, and yet, across the vast, incomprehensible stretches of evolutionary time, the strategy heavily persists. It dominates. Why? Because in the ruthless, unforgiving math of the natural world, biological deterrence absolutely does not require perfection. It only requires a slight statistical advantage. If the dramatic act of inflation successfully dissuades enough predators, just often enough, to allow the fish to successfully breed, then the complex genes encoding that bizarre, violent reflex will endure forever. The horrific, fatal failure in individual, isolated encounters absolutely does not negate the overwhelming mathematical success of the strategy across the span of entire generations. In the quiet, exhausted aftermath of an encounter where the predator simply gives up and swims away, the surviving pufferfish begins a slow, agonizing process of recovery. It deflates incredibly slowly, cautiously expelling the massive volume of water through highly controlled, rhythmic muscular contractions. The rigid, terrifying spines slowly fold backward, flattening perfectly against the skin. The massively distended body slowly returns to its compact, streamlined, hovering form, and the exhausted fish tentatively, nervously resumes its cautious navigation of the dark reef corridors. The terrifying memory of the massive attack permanently imprints itself deep onto the fish's neural circuits, actively adjusting its internal sensitivity thresholds for all future, life-saving responses. The sprawling reef slowly regains its deceptive, glittering calm. The vibrant coral sway gently in the invisible current, and the small invertebrates resume their endless grazing. And somewhere deep within that massive, shifting mosaic of life and color, drifts a small pufferfish. It appears incredibly docile, innocent, and almost comical in its tiny, compact form. But deeply hidden beneath that unassuming, gentle exterior lies a massive, highly complex system of layered, violent defenses, balanced precariously and perfectly between a brilliant, physical bluff and absolute biochemical lethality. The true, deep fear embodied in the act of inflation is not simply the fear of being eaten by a predator. It is a cold, terrifying biological recognition that defense itself can instantly become the ultimate exposure when the illusion finally fails. The massive spike sphere that promised absolute safety can instantaneously become a helpless, immobile target if the hunter simply refuses to blink. And in that terrifying, physical realization lies a much deeper, profound truth about survival in the ruthless depths of the ocean. Absolutely no single, isolated strategy ever guarantees permanence. Every single evolutionary adaptation carries a massive hidden cost. Every grand biological illusion carries a terrifying, fatal risk. Yet the pufferfish endlessly endures, acting as a living, breathing testament to the brilliance of evolutionary compromise. Its grand defense may occasionally, violently falter in individual horrific moments, but across the vast, endlessly shifting calculus of life on the coral reef, the delicate, spiked balance holds just long enough. The sprawling, sunlit corridor of the coral reef rapidly collapses into a jagged, suffocating maze of limestone and deep shadow. To a passing parrotfish, this intricate architecture is the ultimate sanctuary. For millions of years, the survival of small reef fish has depended entirely on their ability to instantly dart into these impenetrable fortresses of stone the moment a shadow passes overhead. The deep, winding crevices offer absolute protection from the massive, high-speed predators that patrol the open blue. But as the parrotfish casually navigates the tight space between two massive, towering coral buttresses, the fundamental rules of the ocean violently betray it. Without a single ripple of warning, a slender, patterned head materializes directly out of the stone. The parrotfish frantically attempts to reverse its momentum, but it is already far too late. There is no distant, ominous silhouette to interpret. There is no gradual, high-speed approach across a vast expanse of open water. The predator is already inside the architecture. It is already deeply embedded within the sanctuary. In these incredibly tight, restrictive reef spaces, distance is not measured in yards or meters. It is measured in mere body lengths, and survival is definitively decided in fractions of a completely unforgiving second. The sea snake does not need to engage in exhausting, prolonged pursuit when the unyielding walls of the environment itself actively compress the encounter. To fully grasp the terror of the specific hunter, one must understand that sea snakes are perfectly, meticulously built for the absolute extremes of confinement. They are not shaped like the muscular torpedoes of the open ocean. Their bodies are completely laterally compressed, flattened from side to side like heavy, living ribbons of muscle. This extreme physical adaptation allows them to seamlessly slip through incredibly narrow gaps between branching staghorn corals and slide deep beneath crushing limestone overhangs where the bulkier, heavy-jawed predators physically cannot follow. Their tails are not the crescent-shaped thrusters of a tuna or a shark. They are highly modified, widened into flat, paddle-like oars. This provides a snake with astonishing, pinpoint maneuverability rather than raw, blinding speed. It enables perfectly controlled, hairpin turns in incredibly tight spaces where a single, clumsy miscalculation would mean a fatal collision with razor-sharp coral. Unlike the great pelagic hunters that rely entirely on velocity across the open water, sea snakes exploit pure geometry. To the sea snake, the massive, complex reef is absolutely not an obstacle. It is an amplifier. The parrotfish only senses the terrifying hydrodynamic turbulence of the strike after the snake's long, muscular body has already curved tightly around a jagged coral spur. The visual system of a reef fish is heavily tuned by evolution to detect sudden, high-contrast movement against the complex backgrounds of the reef. But inside these incredibly tight, shadowed corridors, movement and physical structure seamlessly blend into a single, confusing field of shifting color. The sea snake's intricately patterned scales perfectly mimic the broken, dappled light and the chaotic textures of the reef surfaces, aggressively disrupting its physical outline. The camouflage utilized here is not about rendering the animal invisible across a vast, open distance. It is about total cognitive confusion at arm's length. Then comes the strike. It is not overly dramatic in its physical amplitude, but it is utterly devastating in its extreme proximity. Sea snakes possess small, fixed front fangs located at the very front of their upper jaw, directly connected to highly specialized glands that pump out some of the most potent, lethal neurotoxins on the planet. The strike is a lightning fast-forward snap of the head. When the fangs pierce the scales of the parrotfish, the biochemical warfare is instantaneous. These highly complex toxins are explicitly designed to aggressively interfere with neuromuscular transmission. They rapidly flood the prey's bloodstream, actively binding to the microscopic receptors located at the very synapses of the nerves, completely blocking the essential chemical signals and preventing any further muscle contraction. If this venom were injected out in the vast, open water, a terrified fish might attempt a final, desperate sprint, swimming wildly until the paralysis slowly took hold and it drifted helplessly into the blue. But inside a dark, narrow reef crevice, the physical escape vectors are completely blocked by towering limestone walls and the unforgiving, living branches of coral. The paralysis does not merely cause weakness. In this highly confined space, paralysis is absolute claustrophobic entrapment. This extreme lack of space violently alters the expected behavior of both the predator and the prey. Small reef fish almost entirely rely on rapid, explosive bursts of anaerobic acceleration to reach the safety of the rock. Their incredibly dense bodies are biologically designed for this exact kind of explosive output, allowing them to make sudden, life-saving darts into the tightest crevices. But what happens to the prey's brain when the lethal predator actually originates from deep within those exact same safe crevices? The entire defensive reflex violently, totally collapses. The ultimate shelter instantly becomes the ultimate threat. The reef's labyrinthine complexity, which for the entire history of the ocean has served as a guaranteed refuge from the larger, open-water hunters, suddenly turns into a dark, inescapable trap when it is occupied by a slender, venomous specialist. But the physiological miracles of the sea snake extend far beyond its lethal venom and its flattened body. This creature is an evolutionary invader. It is a terrestrial reptile whose ancient ancestors walked on the land, returning to conquer the sea. Because of this, it does not possess gills. It must breathe air. To survive in this crushing alien environment, sea snakes have evolved a massive, single lung that extends almost the entire length of their elongated bodies. This astonishing anatomical feature functions not only for prolonged, deep water respiration, but crucially as a highly sensitive, internal organ of buoyancy control. By precisely modulating the volume of air trapped within this massive lung, the sea snake achieves flawless, fine-tuned positioning within the water column. It can hover perfectly in place, suspended flawlessly in the middle of a narrow, jagged passage, without ever needing to constantly beat its tail or move its body. This terrifying stability allows the snake to remain absolutely, perfectly motionless in the dark, expertly conserving its precious energy and oxygen while patiently awaiting the erratic movement of an unsuspecting prey. The predator does not advertise its deadly presence through any unnecessary, wasteful motion. It simply becomes another silent, waiting element of the stone. The unbearable tension in these encounters is entirely spatial. In the open ocean, a terrified prey animal may have a luxury of frantically calculating distance, speed, and trajectory. But inside a dark reef corridor barely wider than the predator's own body, all physical options vanish instantly. If the parrotfish attempts to turn violently to the left, its face smashes into unyielding limestone. If it turns desperately to the right, it impales itself on the sharp, living branches of the staghorn coral. Attempting to throw its body into reverse risks a catastrophic collision that will completely kill its momentum. The sea snake flawlessly exploits this extreme spatial compression. It executes its venomous strike at the exact, terrifying millisecond when the prey's internal, biological escape calculus completely fails. Yet, within this apparent, overwhelming advantage lies a severe, deeply ingrained biological constraint. The narrative reversal here is profound. Sea snakes are, and always will be, air-breathing reptiles permanently tethered to the surface of the ocean by unforgiving physiological necessity. Every single dive they make is an agonizing countdown dictated entirely by their internal oxygen stores. And when a snake ventures deep into the most intricate, suffocating interiors of the coral reef to hunt, reaching the surface quickly for a life-saving breath can suddenly become incredibly challenging. The exact same narrow, winding spaces that perfectly favor their lethal ambush can instantly complicate their own retreat. A sea snake that slithers too deeply into a massive, branching coral head actively risks fatal entanglement or severe, lethal delay during its desperate ascent to the air. Moreover, their highly potent venom, specifically optimized to instantly shut down the nervous systems of small, fast-twitch fish and eels, is incredibly, metabolically costly for their bodies to produce. A missed strike is not merely a lost meal. It represents a massive, dangerous waste of biochemical investment. Unlike the massive pelagic predators that can simply rely on raw, brute force to capture their prey, sea snakes must constantly, perfectly balance their lethal precision with extreme restraint. They absolutely cannot afford to engage in wild, indiscriminate biting in these confined quarters. Every strike must be absolute, and the vulnerability of the sea snake deepens even further when you consider the sheer architecture of the trap. The narrow corridor prevents the prey from escaping, but also prevents the snake from easily turning around. If a much larger, highly aggressive predator suddenly enters a corridor behind the snake, the venomous hunter is instantly trapped by its own hunting ground, forced into a desperate backward retreat. But the true, breathtaking complexity of the sea snake's existence is revealed through its bizarre interactions with the rest of the reef community. Many species of reef fish actually recognize the terrifying sea snake not solely as a lethal predator, but occasionally as an incredibly valuable, inadvertent ally. As the sea snake meticulously probes the deepest, darkest crevices of the limestone for its hidden prey, its slithering body inevitably flushes out dozens of small crustaceans, terrified hiding fish, and hidden eels that other, larger predators desperately want to capture. Massive groupers and lightning-fast jacks will actively trail behind the hunting sea snake at a cautious, calculated distance, ruthlessly exploiting the widespread panic and physical disturbance caused by the serpent's deep search. The solitary, venomous hunter unknowingly becomes a focal point of a highly dynamic, opportunistic hunting network. Its mere presence triggers massive, secondary predation events all around it. The reef reorganizes itself around the snake's movement. In some specific ecosystems, tiny, brave, clean wrasses will actively approach the highly venomous sea snakes, brazenly picking off dead skin and irritating marine parasites directly from their patterned scales. The lethal hunter, fully capable of executing a strike that would instantly kill the tiny fish, completely tolerates these small, helpful attendants. Extreme, close-range danger peacefully coexists with intimate, biological symbiosis. The heavy pressure of the reef actively compresses these interactions not only into violent conflict, but into bizarre, highly evolved cooperation. Still, for the terrified parrotfish currently caught deep within the dark corridor, there's absolutely no alliance to be found. The neurotoxin spreads through its tiny bloodstream with catastrophic, terrifying speed, aggressively shutting down the electrical pathways and completely disrupting all muscular control. The frantic, desperate beating of its pectoral fins slowly stutters, weakens, and completely ceases. Its gill movements slow to a useless, agonizing crawl. The sea snake's jaws, though appearing relatively small, firmly secure the fully immobilized prey. Because of the extreme lack of physical space within the crevice, the snake must begin the slow, arduous process of swallowing the fish head first, actively streamlining the bulky prey to allow for smooth ingestion within the tight, restrictive limestone tube. The predator must consume the meal quickly and efficiently, because the relentless countdown in its massive lung is ticking. The absolute demand for atmospheric oxygen is steadily, heavily building in its blood. Once the prey is swallowed, the snake slowly, methodically backs out of the dark labyrinth, its body undulating with incredible grace as it angles upward toward the distant, shimmering blue ceiling of the ocean. Behind it, the sprawling reef instantly returns to its deceptive, beautiful calm. The massive coral polyps extend their delicate, stinging tentacles into the passing current, blindly filtering the microscopic plankton. Small, brightly colored fish hesitantly emerge from their hiding spots, nervously resuming their endless grazing along the sunlit surfaces. Yet, within this incredibly intricate, sprawling architecture, a heavy, invisible tension permanently persists. Every single dark crevice, every shadowed overhang, and every narrow limestone gap may conceal a coiled ribbon of pure muscle and lethal toxin. The sea snakes represent the ultimate, perfect fusion of ancient terrestrial ancestry and highly specialized marine evolution. Their smooth, overlapping scales are perfectly designed to drastically reduce friction as they slide against the razor-sharp coral. Their highly specialized sublingual salt glands work tirelessly to actively excrete the massive amount of excess sodium they ingest, allowing for prolonged, permanent residence in the harsh, highly saline environment. They beautifully embody the very concept of extreme evolutionary compromise, carrying massive, fragile lungs into a high-pressure realm entirely dominated by gills. That single, monumental compromise heavily shapes every aspect of their behavior. They hunt with terrifying, unmatched efficiency within the most constrained, suffocating spaces on Earth, but they must always endlessly account for the long, vertical axis leading back up to the air. Predators of the sea snakes certainly exist as well. Massive tiger sharks and certain highly specialized raptors, such as sea eagles, actively target them. These specific predators possess either a natural immunity or a highly evolved resistance to the snake's lethal venom. Out in the vast, open water, the snake's slender, ribbon-like form offers absolutely zero physical defense beyond its toxicity. It cannot outswim a shark. It cannot fight an eagle. Thus, the incredible complexity of the reef not only aids the snake in its lethal hunting, but it actively provides its only real protection for the much larger, more powerful threats that roam the sea. For the sea snake, physical confinement is both its deadliest weapon and its ultimate, impenetrable shield. In the end, it is this extreme, close-range danger that perfectly defines the sea snake's dark domain. The coral reef is not a passive backdrop for the violence. It is a highly active, complicit instrument, violently narrowing all physical movement until a fatal encounter becomes an absolute, mathematical inevitability. The prey hunted by the sea snake do not experience the grueling, lung-burning horror of prolonged pelagic chase. They do not stare in terror at a distant, rapidly approaching silhouette. They simply turn a corner in the dark and suddenly encounter a lethal predator that is already waiting deep within the very center of their chosen refuge. The fear is profoundly immediate, born entirely of suffocating proximity rather than high-speed pursuit. And as the bright, tropical light filters softly down to branching coral, beautifully illuminating the suspended particles of sand, the vast reef appears deeply tranquil and endlessly peaceful once more. Yet deep within its hidden corridors, the physical concept of space itself actively conspires with ancient, highly evolved venom, permanently compressing the illusion of infinite possibility into a single, terrifying, irreversible moment. The water fractures into violent motion before the prey even understands why it is running. One instant, the squid is suspended flawlessly in the vast, featureless expanse of the pelagic blue. Microscopic chromatophores are pulsing faintly across its translucent mantle in slow, rhythmic waves of silent communication. It is at peace in the endless water column, an organism perfectly adapted to the open void. And in the very next instant, the entire geometry of space completely collapses inward. A dark shadow crosses rapidly from the sunlit surface above. Another streaks aggressively from the left flank. A heavy, rhythmic pressure ripple surges upward from the crushing depth below. There is no jagged coral reef to desperately anchor against. There is no sandy seabed to press its body into. There is no tangled forest of kelp to dissolve within. The open ocean offers the illusion of infinite freedom and unmatched speed, but absolutely denies shelter. The open water is a completely naked arena. The squid's highly complex nervous system instantly ignites. Frantic survival impulses fire down from bizarre, ring-shaped brain wrapped directly around its esophagus, routing emergency signals straight to the heavily muscle-mantled prime for explosive escape. Jet propulsion erupts in a sudden, violent pulse. The highly flexible siphon located beneath its head is instantly angled backward. Water is expelled with the explosive, concussive force of a biological cannon. Velocity violently spikes, tearing the squid away from its original position. But the sea around it is no longer empty space. It is rapidly, systematically closing. Squid are biological machines built from the ground up for terrifying, instantaneous acceleration. Their massive muscular mantle acts as a living, breathing, high-pressure pump. It draws a massive volume of water into an internal cavity, seals the edges tight, and then violently ejects that water through a narrow, highly controlled funnel. This flawless mechanism directly converts raw muscular contraction into massive forward thrust through the unforgiving laws of Newtonian reaction. Intricate layers of circular and radial muscle fibers perfectly coordinate to regulate the rapid intake and the explosive expulsion, producing blinding bursts of speed that can easily outpace almost any fish in the ocean during a short, desperate sprint. Their body is hyper-streamlined, shaped exactly like a missile. Two triangular fins stabilize the chaotic direction of flight, while their 8 arms and 2 feeding tentacles trail closely behind them with absolute aerodynamic discipline. Yet, this blinding, rocket-like propulsion comes at a massive, ultimately devastating metabolic cost. Jetting is energetically expensive to a degree that defies logic. It is entirely driven by fast twitch, anaerobic muscle fibers that immediately begin to accumulate highly toxic lactic acid. A healthy squid can easily outrun a single, solitary predator in a straight-line sprint, but absolutely cannot outrun the fundamental laws of physics. In a one-on-one duel, escape is a beautiful, calculated choreography of speed. The squid senses an approaching hunter through highly advanced statuses, internal organs that precisely detect orientation, gravity, and the slightest changes in acceleration. It reads the incoming threat through millions of microscopic mechanoreceptors embedded directly in its delicate skin, registering minute changes in water pressure. It locks onto the predator using massive, incredibly complex eyes that rival, and in some ways exceed, the resolution of vertebrate optics. It executes its defense instantly. It shifts its entire body hue in the blink of an eye. The chromatophores rapidly expand, flushing its mantle dark to match the depths. Reflective cells known as iridophores manipulate the ambient light to violently distort its physical outline. And then, the ultimate illusion, a massive cloud of dense ink erupts from a specialized sac located near the gut. But this is not merely a smokescreen. The ink, bound heavily with mucus, actively forms a cohesive, three-dimensional mass in the water known as a pseudomorph, a literal, physical decoy that mimics the exact size and shape of the squid. The predator lunges viciously at the dark, floating silhouette, biting into nothing but bitter melanin and seawater, while the actual squid completely vanishes in a blinding burst of jetting velocity, leaving only a ghost behind. In these isolated, solitary encounters, survival almost always favors a cephalopod's unmatched agility and biological deception. But when highly intelligent predators suddenly converge from multiple vectors at once, the elegant calculus of survival violently mutates into absolute chaos. A massive school of pelagic fish closes in from the eastern flank, driving the squid violently upward toward the bright surface. A highly coordinated pod of dolphins arcs in from the periphery, actively hunting through echolocation. They are firing rapid acoustic pulses into the water, mathematically mapping the three-dimensional space with terrifying precision. Directly beneath the squid, a massive tuna slices upward from the cold dark, its heavy red muscle tissue burning hot, fully prepared to sustain a grueling, hour-long pursuit. The limitless open water instantly becomes a shrinking sphere of absolute threat. Every single jet burst violently drains the squid's precious oxygen. Every desperate, evasive maneuver actively narrows its remaining options. Unlike the fish and the mammals hunting it, the squid entirely lacks any rigid skeletal support. Its body is purely hydrostatic. It relies entirely on the delicate balance of internal fluid pressure to maintain its physical shape and structural integrity, subjecting the soft hydrostatic architecture to sustained, high-speed, multi-directional movement risks, completely destabilizing the animal's physical form. The resulting confusion within the squid spreads not as a conscious, emotional panic, but as a catastrophic physiological and neurological overload. The squid's incredibly advanced neural architecture is entirely decentralized. Massive bundles of nerves, known as ganglia, extend deep into every single one of its arms. This bizarre, alien design allows for semi-autonomous movement. The arms can literally taste, touch, and react to their environment without ever needing permission from the central brain. This permits extraordinary physical flexibility and lightning-fast reflex arcs, but under the crushing weight of multi-directional assault, it produces violently conflicting motor commands. One highly perceptive arm senses the incoming pressure wave of a dolphin and instantly signals for a violent lateral evasion to the left. Simultaneously, the central brain, visually tracking the rapidly ascending tuna, frantically commands a mantle to contract for maximum vertical thrust toward the surface. The body fights itself in the water. Even the deployment of the famous ink cloud violently betrays the squid in this specific scenario. The ink may successfully obscure the squid from the visual targeting of the tuna, but the heavy chemical composition of the melanin and the mucus acts as a massive, screaming beacon in the water. It reveals the squid's exact panic position to the highly tuned olfactory senses of the other predators navigating the scent gradients. What begins as a brilliant, evolutionary defense mechanism instantaneously transforms into a glowing target painted squarely on its back. The internal energy reserves completely deplete at a terrifying rate. Squid utterly lack the sustained, aerobic endurance of the heavily muscled tuna or the air-breathing dolphins. The squid's blood is fundamentally different. It is driven by hemocyanin. It relies entirely on copper, rather than iron, for oxygen transport. This makes their blood run a haunting, alien blue. It is an incredibly efficient system in freezing, heavily oxygenated deep waters, but it is notoriously fatally incapable of delivering oxygen fast enough under conditions of extreme, sustained physical exertion near the warmer surface. As the heavy, toxic lactate rapidly accumulates in the thick mantle muscles, the biological pump begins to fail. The efficiency of the muscular contraction violently drops. The once smooth, explosive jet propulsion degrades into erratic, sputtering bursts. The squid's blinding speed falters. Panic, if it can be truly defined as such in a cephalopod, is simply the visible, tragic physical manifestation of total metabolic collapse. The surrounding predators ruthlessly exploit this downward physiological spiral. The dolphins expertly herd the exhausted squid into an increasingly tight, frantic cluster, deliberately compressing its physical escape space. Their incredible intelligence is not an abstract concept. It is purely ecological. It is shaped by ancient, cooperative hunting strategies refined over thousands of generations. By violently driving the prey toward the absolute ceiling of the ocean surface, they completely eliminate all vertical escape routes. The air above becomes an impenetrable wall. The massive tuna accelerate from the deep, utilizing their perfect counter-shaded bodies to remain entirely invisible against the dark water until the final lethal surge. Each completely different predator species imposes a different, inescapable physical constraint, and together, they seamlessly weave a closing, three-dimensional lattice of high-speed motion. At first glance, this scenario seemed completely terminal. The squid celebrated. Blinding speed becomes totally irrelevant the exact moment its directionality is compromised. The open water, which just a moment ago represented infinite freedom, is now absolute, terrifying exposure. Yet, within the absolute center of this violent vortex of pursuit lies a much subtler, breathtaking adaptation that is rarely acknowledged. Many species of pelagic squid do not actually face these massive, multi-directional assaults alone. Deep beneath the chaotic surface of their apparent individuality lies a magnificent biological phenomenon known as dynamic schooling. While squid entirely lack the rigid, mathematically precise cohesion of a massive bait ball of sardines, they are highly capable of forming incredibly synchronized, fluid aggregations that dynamically shift their shape, size, and density in direct, immediate response to an incoming threat. The chromatophores covering their bodies begin to flash in violently coordinated, blinding waves, transmitting complex visual signals across thousands of bodies in mere milliseconds. These rapid, shifting color patterns are not mere displays of panic. They are massive, broadband information exchanges. When the predators approach from multiple, conflicting directions, the individual squid rapidly align with one another, instantly creating a massive, shifting, strobing mass that completely confuses the highly tuned targeting algorithms in the predator's brains. This is the great evolutionary reversal of the cephalopod, the exact same decentralized, hypersensitive nervous system that violently fragments and collapses under solitary panic suddenly transforms into a massive, collective amplifier when surrounded by its own kind. The movement patterns of the entire school flawlessly synchronize, actively generating a flickering, chaotic wall of soft bodies whose highly reflective iridophores actively scatter the penetrating sunlight in completely unpredictable, blinding directions. Predators that rely heavily on visual locking, like the massive tuna, struggle immensely to isolate and track a single, definable target within the rapidly shifting, strobing swarm. The dolphins rely on acoustic mapping, are suddenly forced to constantly recalibrate their highly complex sonar. The returning echoes are violently distorted and scrambled by the overlapping layers of thousands of soft, fluid bodies. The tuna frequently overshoot their targets, violently slicing through entirely empty water as a collective group of squid effortlessly shifts out away like a living, intelligent cloud of smoke. Even the deployment of ink dramatically transforms under the power of collective use. When dozens of individual squid release their ink sacs simultaneously, they do not create a simple, floating decoy blob. They create a massive, volumetric fog of war. It becomes a broad, impenetrable field of absolute opacity, hanging heavily in the water column. Within this temporary, manufactured darkness, the squid rapidly reverse their direction. Some individuals will even swim aggressively toward the incoming predators for a terrifying fraction of a second, perfectly exploiting the temporary blind zones created in the predator's pursuit paths. What appears to the untrained eye as blind, chaotic panic is actually a state of highly tactical entropy. It is a deliberate, calculated increase in the environmental noise specifically designed to actively destabilize the coordination of the hunters. But this massive collective strategy carries severe, life-threatening costs. Grouping tightly together drastically increases the fierce internal competition for limited oxygen, and the sheer, massive spectacle of the strobe-flashing school inevitably attracts even larger, more devastating predators from miles away. Massive whales and oceanic sharks highly capable of penetrating confusion through sheer, undeniable physical force. The energy expenditure multiplies exponentially as every single individual within the cloud frantically jets just to maintain its exact position within the dynamic, shifting mass. The brutal metabolic strain remains acute. The sea absolutely never grants an unlimited reprieve. As the oxygen debt deepens to catastrophic levels and the heavy lactate begins to physically shut down their mantles, some highly specialized squid resort to an absolute final, breathtaking adaptation, bioluminescence. Microscopic photophores embedded deeply within their translucent skin begin to emit highly controlled, radiant flashes of blue light. They actively mimic the exact wavelength and intensity of the downwelling sunlight filtering from above, engaging in a desperate, brilliant strategy known as counter-illumination. By perfectly matching the brightness of their own bodies to the ambient light conditions of the surrounding ocean, the squid completely erases its physical silhouette when viewed from the dark depths below. In the sheer chaos of a multidirectional assault, this living camouflage can successfully disrupt the upward attacks from the massive tuna and the deep-diving sharks that rely entirely on contrast detection. Yet, bioluminescence requires incredibly precise, demanding neural control and a massive, continuous investment of biological energy. Overusing the light-producing organs or slightly miscalculating the ambient brightness may instantly reveal rather than conceal the animal. The open ocean is absolutely not the empty space it appears to be. It is a highly complex, fiercely structured fluid arena completely governed by invisible thermoclines, violent current shears, and massive pressure gradients that drastically alter how sound and light travel. The apex predators navigating this massive arena flawlessly exploit physical features that are completely invisible to the struggling prey. The highly intelligent dolphins may actively drive the squid toward invisible convergence zones where two massive ocean currents violently collide, completely compressing the squid's escape trajectories against an invisible wall of water pressure. The massive tuna seamlessly utilize the distinct thermal layers of the ocean to actively enhance their own muscle efficiency, staying in the warm water while driving the squid into the exhausting, freezing deep. The squid must constantly, frantically interpret all of these invisible, shifting structures while under most extreme, life-threatening duress imaginable. And still, sometimes, against all biological and mathematical odds, survival emerges directly from the jaws of collapse, when the internal energy violently drains to the absolute point of near failure, and the manhole can no longer pump. Some squid will completely abandon propulsion altogether. They simply stop, they let go, and they begin to sink, reducing their hydrodynamic movement signature entirely and abruptly to zero. The massive, high-speed predators, whose brains are fully anticipating a continued, frantic forward acceleration, violently overshoot the mark. Their own massive momentum carries them entirely beyond immediate reach. In the brief, terrifying silence that follows the passing of the hunters, the squid slowly, agonizingly regains control. Its exhausted mantle muscles contract minimally, just enough to slowly restore its physical orientation in the water column. What heavily appears to be a total surrender to death is, in reality, a state of profound, strategic stillness. The incredibly soft hydrostatic body, which was just a moment ago violently destabilized by the frantic, chaotic jetting, slowly recenters itself entirely under gravity's subtle, pulling embrace. In a violent medium where high-speed movement instantly attracts lethal attention, total immobility can become the ultimate, perfect camouflage. The staggering ecological implications of this daily, massive struggle ripple outward across the entire planet. Pelagic squid occupy a massive, central trophic position in the global food web. They're the great biological converters of the sea, transforming the microscopic zooplankton and the tiny baitfish into the massive, dense biological biomass that literally fuels the entire upper tier of the ocean's predators. Their constant extreme vulnerability heavily sustains the massive dolphin pods, feeds the endless tuna migrations, and supports the deep-diving sperm whales, which in turn actively regulate the global fish populations and drive the massive nutrients cycling across entire planetary ocean basins. These terrifying, multi-directional predation events are absolutely not random anomalies. They are the massive, structural, thermodynamic forces that actively shape the architecture of all pelagic ecosystems. The frantic, terrifying panic spiral of a single, exhausted squid perfectly reflects the broader, brutal thermodynamic reality of life in the open water. Energy constantly, violently flows upward through risk. The open water promises infinite freedom, but it demands absolute, unrelenting vigilance in return. Blinding speed offers a promise of escape, but aggressively consumes life from the inside out. When the shadows approach from multiple directions and the water begins to violently close in, The squid violently confronts the absolute limits of its own evolutionary design. And yet, deeply embedded within those extreme physical limits lies an astonishing alien adaptability. Instantaneous collective signaling, volumetric chemical camouflage, brilliant bioluminescence, and rapid metabolic recalibration. The confusion may rise to a deafening pitch. The energy may totally drain away. The blue blood may turn toxic with fatigue. But the biological story absolutely does not end in inevitability. It unfolds endlessly in a beautiful, terrifying, fluid negotiation between total chaos and absolute control. The sea never, ever empties entirely. It simply waits, endlessly layered, incredibly immense, and always ready to close again. The natural world is an endless theater of survival, where every adaptation tells a story of life, death, and incredible resilience. To uncover more of these hidden battles and explore the untouched corners of our planet, make sure to subscribe to Earth's Documentary. Hit the like button, leave a comment below with your favorite moment, and turn on notifications so you never miss a descent into the wild.